Look up at the night sky, and what do you see? Pinpricks of light scattered across an immense, dark canvas. For centuries, we've been captivated by the stars, their brilliance, their stories, their sheer cosmic grandeur. But what about the space between them? That profound, seemingly empty darkness stretching across light years. We often think of it as nothing, a void. A great cosmic absence. But what if we've been looking at it all wrong? What if that emptiness isn't empty at all? What if the void between stars isn't a blank space, but the most information-rich region of the entire universe, holding even more data, more secrets, more story than the stars themselves? This isn't just a poetic thought. It's a possibility that's emerging from the frontiers of modern physics, cosmology, and information science. We're beginning to understand that what we call empty space is in reality a seething, dynamic, and astonishingly complex medium. Quantum particles flicker in and out of existence. Dark matter and dark energy weave invisible architectures that guide the fate of galaxies. Spacetime itself may act like a cosmic hard drive, storing information in ways we're only starting to imagine. This idea doesn't just challenge what we know, it turns our entire understanding of reality inside out. It suggests that the true heart of the universe's mystery may not lie in the shining stars, but in the profound depths of the darkness between them. In this video, we're going to journey into that darkness. We'll explore how nothingness might actually be everything. We'll dive into mind-expanding concepts like the holographic principle, quantum foam, and the hidden signatures of the Big Bang still echoing across the cosmos. We'll question what information really means on a universal scale and reconsider our place within this vast, connected tapestry of existence. So prepare to shift your perspective. Open your mind to the extraordinary, because we're about to venture into the unknown where the void isn't the end of the story, it's just the beginning. When we gaze up at the night sky, the darkness between stars appears as a perfect, absolute nothing, a void in the truest sense of the word. But this impression is one of the universe's most elegant illusions. What we perceive as empty space is, in reality, a vibrant and dynamic arena, humming with activity and filled with entities that defy our conventional understanding of nothingness. To even begin exploring the idea that this void could hold more information than stars, we first have to completely redefine what we mean by empty. At the heart of this redefinition is quantum field theory, which tells us that there is no such thing as a true vacuum, a complete absence of everything. Instead, what we call empty space is seething with quantum fluctuations. Think of it like this. Imagine the fabric of spacetime as a vast, calm ocean. On the surface, it might look still and serene, but if you could look at the subatomic level, you'd see a boiling foam of energy, a constant, frantic dance of particles and antiparticles spontaneously popping into existence and then annihilating each other almost instantly. These are virtual particles, and they are a fundamental feature of the quantum vacuum. They borrow energy from the universe for a fleeting moment, thanks to the Heisenberg uncertainty principle. And in that brief flash of existence, they create a background of energy that permeates every single cubic centimeter of space, no matter how empty it seems. This isn't just a beautiful mathematical idea, it's a physical reality we can actually measure. One of the most compelling demonstrations of this is the Casimir effect. In the 1940s, the Dutch physicist Hendrik Casimir predicted that if you placed two uncharged, perfectly smooth metal plates extremely close together in a vacuum, they would be gently pulled toward each other. Why? Because the plates are so close that they limit the kinds of quantum fluctuations that can occur in the space between them. The fluctuations outside the plates, however, continue unchecked. The greater external pressure literally pushes the plates together. This experiment has been performed, and it works exactly as predicted. It provides tangible, measurable proof that the vacuum is not passive. It exerts a force. It's alive with transient energy. Beyond this quantum foam, the void is also filled with the enigmatic presence of dark matter and dark energy. We can't see them, we haven't directly detected them with any instrument, yet we know they are there by their profound gravitational effects on the universe. Dark matter forms an invisible scaffold around galaxies, providing the extra mass needed to hold them together as they spin. Dark energy is the mysterious force causing the expansion of the universe to accelerate. These entities are not concentrated in stars or planets. They are diffuse, permeating the vast intergalactic spaces. They are a fundamental part of the void's composition, meaning that what looks like a barren expanse is actually saturated with these invisible, influential components. So when we say void, we are not talking about a sterile nothingness. We are talking about a complex, energetic medium, a rich broth of quantum potentiality, dark matter, and dark energy. This shifts our perspective entirely. Emptiness is not an absence, it is a presence. It is not a blank slate, but a dynamic and information-rich substrate. This foundational understanding is crucial because it allows us to begin asking the extraordinary question: if this is what the void is made of, how much information could it possibly contain? But if the void is not empty, then what exactly is it filled with? To answer that, we need to tackle a concept that is just as fundamental, yet just as abstract: information itself. We throw that word around all the time in our digital age. We talk about storing information on our phones, consuming information from the news, transferring information across the internet. But in a cosmic sense, what is it? Is it just a human concept, or is it a real, physical property woven into the fabric of the universe, as real as matter or energy? This question was revolutionized in 1948 by a brilliant mathematician and engineer named Claude Shannon. Working at Bell Labs, Shannon published a landmark paper that founded what we now call information theory. Before Shannon, information was thought of in terms of its meaning, the message it carried, but Shannon made a stunningly simple yet profound shift. He separated the meaning of a message from its pure, mathematical information content. He wasn't interested in whether a message was sad or joyful. He was interested in how to measure it, transmit it, and compress it without error. Shannon's fundamental unit became the bit, a binary digit representing a single choice between two equally likely possibilities, a yes or a no, a 1 or a 0. Think of it like flipping a coin. A fair coin flip has exactly one bit of information because there are two possible outcomes, and before you look, you are completely uncertain about the result. The information, in Shannon's view, is directly related to this uncertainty. The more uncertain you are about the outcome, the more information you gain when you learn what it is. A coin that always lands on heads has zero information content because there's no surprise, no news. But a random coin flip is packed with one full bit of news. Now let's scale this idea up from a coin to the cosmos. If information is a measure of uncertainty and the number of possible states a system can be in, then the universe is the ultimate information processing system. Every particle, every field fluctuation, every ripple in spacetime can be thought of as holding or conveying information. A single electron with its spin that can be either up or down is like a cosmic bit. The precise configuration of atoms in a distant nebula encodes information about its history and composition. Even the gravitational waves from colliding black holes, which stretch and compress spacetime itself as they travel, are carriers of information telling us about the masses, spins, and energies of those colossal events. This brings us to a crucial and often misunderstood connection: the link between information and entropy. In physics, entropy is a measure of disorder or randomness. A scattered deck of cards has high entropy, a neatly ordered deck has low entropy. But in a beautiful convergence of ideas, it turns out that Shannon's measure of information is mathematically identical to the physicist's measure of entropy. A system with high entropy is one with a huge number of possible microscopic states it could be in. Describing its exact state at any moment requires a lot of information because there's so much uncertainty. A system with low entropy is highly ordered with fewer possible states and thus requires less information to describe. So, where does our void fit into this? We often think of empty space as the most disordered, high-entropy state possible, just random chaos. But paradoxically, the large-scale vacuum of space actually has extremely low entropy. It's incredibly smooth and uniform. If it were high entropy, we'd see energy and matter scattered randomly everywhere, but instead we see vast, cold, empty expanses. This is the puzzle. How can something with such low entropy potentially hold so much information? The answer may lie in the difference between scale. On the large scale, the void is simple and ordered, but on the quantum scale, it is a frenzy of activity, a foam of virtual particles, fluctuating fields, and probabilistic events. This is where the information capacity becomes almost unimaginably vast. Think of it like a modern computer hard drive. The outside of the drive is simple, smooth, and ordered low entropy. But on the inside, on the microscopic platters, there is a universe of complexity. The magnetic domains can be oriented in a near-infinite number of configurations, each representing a different string of ones and zeros, a different piece of information. The void might be the same. Its large-scale simplicity masks a quantum-level hard drive of staggering capacity, where every tiny fluctuation is a bit, and the fabric of spacetime itself is the storage medium. This foundational shift in how we view information, not as abstract ideas but as a physical, cosmological property, is what allows us to even entertain the staggering possibility that the darkness holds more than the light. Now, let's turn our gaze from the profound depths of the void to the brilliant beacons we know so well, the stars. For all of human history, they have been our guides, our muses, and our windows into the workings of the cosmos. They are not just balls of hot gas, they are cosmic storytellers, broadcasting a continuous stream of data about their lives, deaths, and everything in between. The light that travels for millions of years to reach our eyes is packed with a narrative written in the very language of physics. So, what story does a star tell? It begins with its composition. By dissecting starlight through a technique called spectroscopy, astrophysicists can act as cosmic detectives. When starlight passes through a prism or a spectrograph, it splits into a rainbow spectrum. But this rainbow is etched with dark, vertical lines like a unique barcode. Each element in the star's outer atmosphere absorbs light at very specific wavelengths, creating these telltale absorption lines. The pattern of these lines is a direct fingerprint, revealing whether a star is rich in hydrogen, helium, or heavier elements like carbon, oxygen, and iron. This single measurement tells us not only what the star is made of, but also its stage in life. A young star will be primarily hydrogen, the primordial fuel of the universe. An older star may show signs of the heavier elements forged in its core, hinting at its advanced age and the processes happening deep within, and what incredible processes they are. The heart of a star is a continuous information generator. Through the relentless crush of gravity and the blaze of nuclear fusion, hydrogen atoms are slammed together to form helium, releasing a torrent of energy in the process. This energy doesn't just make the star shine, it carries information. The photons of light produced in the core take a fascinating journey, bouncing around for thousands of years before finally escaping the star's surface. When they finally stream out into space, they bring with them an encoded record of the intense conditions and reactions that created them. But light isn't the only messenger. Stars also emit a flood of nearly massless particles called neutrinos, born directly from the nuclear reactions in their cores. Unlike photons, neutrinos barely interact with matter. They fly straight out of the star at nearly the speed of light, offering an almost instantaneous snapshot of the core's activity, unaffected by the layers of gas above. The story a star tells evolves dramatically over its lifetime. A massive star doesn't just fade away, it goes out in the most spectacular information-releasing event imaginable, a supernova. In its final moments, a supernova can outshine an entire galaxy. In that cataclysmic explosion, the extreme temperatures and pressures forge elements far heavier than iron, gold, silver, uranium, and then blast them out across interstellar space. The light echo and the expanding remnant shell of a supernova, which we can observe for centuries afterward, provide a detailed forensic report on the star's final moments, its mass, and the new elements it has seeded into the cosmos for future generations of stars and planets. There is no question that stars are information powerhouses. The data we gather from them has allowed us to piece together the life cycle of stars, map the structure of our galaxy, and even understand the origin of the very elements that make up our bodies. We are quite literally star stuff reading the messages of our ancestors, yet for all their richness, stellar information has inherent limits. It is profoundly localized. Each star is a distinct point source, a brilliant pinprick in a vast, dark ocean. The information it emits is primarily about itself and its immediate surroundings. Furthermore, this information is finite. A star has a limited amount of fuel. It produces a finite number of photons over its lifetime. Once it dies, the stream of new information from that source, aside from its remnant, largely ceases. This brings us to a crucial juxtaposition. On one hand, we have stars, dazzling, information-rich, but isolated and finite points. On the other hand, we have the void, seemingly dark, diffuse, but unimaginably vast and permeated by a dynamic quantum energy that might never cease. The question then becomes not just a poetic wonder, but a serious scientific inquiry. Could the cumulative, subtle, and endless information potential of the void stretching across billions of light years actually surpass the total information output of all the stars that have ever shone? To explore that, we must venture even deeper into the quantum realm, to the very foam of spacetime itself. But if we truly want to grasp the staggering informational potential of the void, we must venture beyond the light of stars and into the heart of darkness itself, to the very fabric of spacetime, where the rules of reality as we know them break down and something far more strange and wonderful takes over. This is the quantum vacuum, and it is anything but empty. In fact, it is the most active, seething, and energetic place imaginable, a realm where the concept of nothing has been completely rewritten by modern physics. This incredible activity is driven by a fundamental feature of our universe called zero-point energy. The name sounds like something from science fiction, but it's a very real and very weird cornerstone of quantum mechanics. The zero point refers to the absolute lowest possible energy state a quantum system can have. In the classical world, if you cool something down to absolute zero, all motion stops. But in the quantum world, even at absolute zero, there is a residual, eternal jitter, a fundamental fizzing and buzzing that can never be removed. This is the zero-point energy, and it means that a perfect vacuum, the complete absence of all particles, is physically impossible. The void is not still, it is a turbulent ocean. This energy manifests as a constant storm of virtual particles, pairs of particles and antiparticles, an electron and a positron, for instance, spontaneously blink into existence, borrowing energy from the vacuum for an almost unimaginably brief moment, only to collide and annihilate each other, returning the energy back to the void. This isn't just a theoretical idea, we see its effects everywhere. It's responsible for subtle shifts in the energy levels of atoms, and as we discussed, it creates the measurable Casimir force. The renowned physicist Richard Feynman once described it as space being so full of these fleeting particles that it resembles a boiling soup, a foam of existence. This is the origin of the term quantum foam, a concept suggesting that at the tiniest possible scales, the Planck scale, spacetime itself is not smooth and continuous but a churning, frothy mess of virtual wormholes and tunnels, constantly fluctuating. Now here is where it connects to information. Every single one of these quantum fluctuations is an event. Each virtual particle pair popping in and out of existence represents a choice, a decision between possible states. Remember our discussion about bits and information. This quantum foam is a universe of bits. The endless, frantic dance of these particles creates a near infinite number of possible configurations across the vast expanse of space. Each fluctuation is like a pixel on a cosmic screen, flickering between 1 and 0 at a staggering rate. The vacuum state, therefore, is not a blank slate but a dynamic, informational substrate of almost limitless potential. Its information density is not in large, obvious structures like stars, but in an unimaginably fine-grained, ubiquitous mist of data encoded in the fields and energies that make up reality itself. This idea finds its most profound expression in the holographic principle, a theory that emerges from the study of black holes. When a black hole swallows matter, what happens to the information that matter contained? According to the laws of quantum mechanics, information can never be truly destroyed. The brilliant physicist Jacob Bekenstein and later Stephen Hawking discovered that a black hole's entropy, which, as we know, is directly linked to its information content, is not proportional to its volume, as you might expect, but to the surface area of its event horizon. It's as if all the information about everything that fell into the three-dimensional black hole is encoded on its two-dimensional boundary. The holographic principle takes this stunning idea and applies it to the entire universe, suggesting that all the information within a volume of space might be stored on its boundary surface. The three-dimensional world we experience could be a projection from a two-dimensional surface encoded at the edge of the universe. And where is that surface? It is the void itself. The vast, dark expanses between galaxies could be that cosmic hard drive platter, with every quantum fluctuation on that surface projecting the reality we see within. So, when we compare the information content, the scales become almost laughably tilted. A star is a brilliant, localized server pumping out data for millions of years. But the quantum vacuum is a server farm that is everywhere, in every single tiny fraction of space, and it has been operating since the first moment of the Big Bang. Its operations are not finite, they are eternal and ubiquitous. The cumulative information potential of all the quantum fluctuations in just a cubic light year of empty space could, in theory, dwarf the total information ever emitted by a star. We are surrounded by an ocean of data, a cosmic internet encoded in the foam of space-time, and we are only just beginning to learn how to read its signals. But our exploration of the void's hidden activity can't stop at the quantum scale. There are even larger, more mysterious forces at work in the cosmos' invisible architects that shape the universe on the grandest scales imaginable. We've detected them not by seeing them, but by witnessing their profound influence on everything we can see. They are the twin enigmas of dark matter and dark energy, and they don't just reside in the void. They are the void's primary ingredients, its most dominant and secretive informants. Let's start with dark matter. Imagine watching a merry-go-round spinning at a playground. The children sitting on the outer edge are whipping around at a tremendous speed, and you'd expect the centrifugal force to send them flying off into the grass. But they don't. They're held firmly in place by the structure of the ride. Now, apply that to a galaxy. Stars on the outer edges of spiral galaxies are orbiting the center at velocities so high that the visible matter, all the stars and gas clouds we can see, doesn't provide nearly enough gravitational glue to hold them in their tracks. According to all the laws of physics we know, these galaxies should be flying apart. The fact that they aren't tells us one thing with absolute certainty. There is something else there, providing the extra mass, the extra gravity. We call this invisible something dark matter. It doesn't emit, absorb, or reflect light. It only interacts with the universe through gravity, and it isn't just sprinkled in. It forms vast, spherical halos that envelop entire galaxies like immense, invisible cocoons, providing the hidden scaffolding upon which the visible universe is built. Now consider the implications for information. This dark matter halo isn't a uniform blob. Sophisticated computer simulations, like the famous Millennium Run or the Illustris TNG project, show us that dark matter forms an intricate cosmic web, a labyrinth of filaments and nodes stretching across the universe. The gravitational pull of this web dictates where galaxies will form, how they will cluster together, and how they will evolve over billions of years. The precise distribution and density of dark matter in a region of space is in itself a massive data set. It's a frozen record of the initial conditions of the universe, a relic of the gravitational collapse that began moments after the Big Bang. By mapping the gravitational lensing effect where the gravity of dark matter bends the light from distant galaxies, we are essentially decoding this hidden information, reading the imprint of the invisible on the visible. The dark matter halo around a single galaxy could contain more informational complexity about the history of cosmic structure than all the visible stars within it. Then there is dark energy, an even more perplexing phenomenon. In the late 1990s, two separate teams of astronomers made a discovery that turned cosmology on its head. By observing distant supernova, they found that the expansion of the universe is not slowing down, as everyone expected due to gravity's pull. It's accelerating. Something is actively pushing space itself apart, and we've named this something dark energy. Think of the fabric of spacetime as the surface of a balloon. Dark energy is like someone steadily blowing more air into that balloon, causing every point on its surface to move away from every other point at an ever-increasing rate. It appears to be a property of the vacuum of space itself, a constant energy density that grows more dominant as the universe expands and becomes emptier. What kind of information could dark energy possibly hold? Its very nature, its relentless and constant push, is a message. It tells us about the fundamental constants of our universe, the rules written into the bedrock of reality that determine its ultimate fate. The strength of dark energy is a number, a value. That value is information. Some theories, like the concept of quintessence, propose that dark energy might not be a constant but a dynamic field that could vary over time or space. If that were true, then the void would be filled with a shifting, evolving energy field, its variations encoding a complex story about the evolution of the cosmos. Even if it is a constant, its mere presence and strength are the most critical pieces of data in the entire cosmic equation, determining whether the universe will end in a heat death, a big rip, or some other unknown destiny. Together, dark matter and dark energy show us that the void is not a passive stage upon which the drama of stars and galaxies plays out. It is an active, dynamic participant. It is the director and the playwright guiding the action through invisible hands. The emptiness between stars is, in fact, overflowing with these enigmatic entities that dictate the shape, size, and fate of everything we hold visible and familiar. They represent a hidden informational layer to reality, a deep data stream woven into the fabric of space itself. To ignore them is to try and understand a movie by only looking at the actors, while ignoring the script, the director, and the very screen it's projected upon. They are the ultimate invisible informants, and they are telling us that the true story of the universe is written in the dark. But to truly push the boundaries of what we think is possible, we must now confront one of the most radical and mind-bending ideas in all of modern physics, a concept that suggests our entire perception of a three-dimensional universe might be nothing more than an elaborate illusion. This is the holographic principle, and if it holds even a grain of truth, it completely redefines the informational supremacy of the void, casting it not as a mere participant in the cosmic story, but as the very stage upon which the entire play is projected. The seeds of this astonishing idea were not sown in the study of empty space, but in the most information-destructive objects we know of, black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, which, as we've established, is a direct measure of its information content, is not proportional to its volume as common sense would dictate. Instead, it is proportional to the surface area of its event horizon. Think about that for a moment. The event horizon is just the spherical point of no return, the black hole's two-dimensional surface. Bekenstein and later Stephen Hawking showed that all the information about everything that ever fell into the black hole, every atom, every person, every planet, is somehow encoded on this two-dimensional boundary. The three-dimensional interior, with its unfathomable density and warped spacetime, is, informationally speaking, redundant. The entire story is written on the surface. This revelation was so counterintuitive that it sparked decades of debate and research, led by visionary physicists like Leonard Susskind and Gerard T. Hooft. They took the black hole information paradox and asked a breathtakingly bold question. If this is true for a black hole, could it be true for the entire universe? What if our magnificent three-dimensional cosmos, with its galaxies, stars, and planets, is actually a holographic projection from a two-dimensional surface encoded at the very boundaries of space? In this view, the universe operates like a cosmic 3D movie. When you sit in a theater, you see a world with depth, objects moving toward you and away from you. But all that information, the entire three-dimensional experience, is actually contained on the two-dimensional film strip running through the projector. The void, the vast darkness at the edge of everything, could be that film strip. This principle utterly inverts our understanding of where information resides. If the holographic principle is correct, then the true information storage of the universe isn't in the stars or the galaxies themselves. It is on the distant, two-dimensional boundary of the observable cosmos. Every event, every particle, every fluctuation within our three-dimensional volume is a projection of data stored on this vast spherical shell. the implications for the void are profound. The empty space between stars is no longer just a medium filled with quantum foam and dark matter. It becomes the physical manifestation of this projected reality. The void is the image, and the information that creates that image is stored on a surface we cannot see or touch. This makes the informational capacity of the void not just large, but conceptually absolute. The amount of information that can be contained within any volume of space is fundamentally limited by the area of its boundary, not its volume. It suggests there is a maximum amount of information that can possibly fit in any given region, a concept known as the Bekenstein bound. When you apply this to the entire observable universe, the math reveals something staggering. All the information needed to describe every particle, every force, and every moment of history could be encoded on a surface with pixels the size of a Planck length, the smallest possible unit in physics. The void we see is the magnificent, projected result of this unimaginably dense data storage happening at the edge of everything. So, when we compare the information content of stars versus the void through this holographic lens, the comparison becomes almost trivial. A star is a beautiful but mere projection, a temporary pattern of light and energy within the volume. The information that defines it, its entire existence and history, is ultimately stored elsewhere, on that fundamental two-dimensional surface. The void is not competing with stars, it is the canvas upon which the stars are painted. This theory challenges the very core of our perception, suggesting that the true reality is a flat, information-dense surface, and the rich, three-dimensional world we experience is a spectacularly detailed hologram. It positions the void, the apparent emptiness, as the central player in the cosmos's grand informational architecture, the final frontier in our quest to understand where and how the universe keeps its deepest secrets. This brings us to a concept that is as fundamental to physics as it is often misunderstood, a principle that governs the ultimate fate of the universe and intimately ties together the nature of stars, the void, and information itself, entropy. Often described as a measure of disorder or randomness, entropy is the star of the show in the second law of thermodynamics, which states that the total entropy of an isolated system can never decrease over time. It's the reason why a hot cup of coffee cools down in a room, why a drop of ink disperses in water, and why we remember the past but not the future. It gives our universe its arrow of time. But here's the beautiful and counterintuitive twist. High entropy, this state of maximum disorder, is also a state of incredibly high information content. To understand why, let's go back to our deck of cards. A brand new deck, fresh out of the box, is perfectly ordered. All the suits are together, all the cards are in sequence. This state has very low entropy. It's also a state that is very easy to describe. You could just say, it's in perfect order, and someone would know exactly what you mean. Now take that deck and give it a really good shuffle. The cards are now in a completely random, disordered sequence. This state has very high entropy. But to describe this new state to someone, to tell them the exact position of every single card, you would need to give them a massive amount of information. You'd have to list every card one by one in its new random position. The high entropy state requires far more information to describe it precisely because there are so many more possible ways for the deck to be disordered than ordered. The information is a measure of the specific disorder. Now let's apply this cosmic lens to our two subjects, stars and the void. A star, like our sun, is a marvel of low entropy. It's a massive, organized, and concentrated sphere of hot gas, with a huge temperature difference between its blazing core and its cooler surface. It's a giant, structured machine steadily burning fuel and radiating energy out into the coldness of space. In the grand scheme of the universe, stars are like those neat, ordered decks of cards. They are pockets of exquisite, temporary order, but this low entropy comes at a cost. Because they are so ordered, their specific state is relatively simple to describe from an informational standpoint. We can model a star's life with a set of equations. Its brilliant light tells a story, but it's a story with a predictable plot. Contrast this with the void. On the largest scales, the cosmos appears smooth and uniform. This was the low entropy starting condition of the Big Bang. But when we zoom in on the quantum scale of the vacuum, we find something entirely different. The quantum foam, with its endless, random fluctuations of virtual particles, is a state of profound chaos and disorder. And as we've just learned, this disorder translates directly into an astronomical potential for information. Every random flicker of a particle is a piece of data. The gravitational influence of dark matter is not a smooth blanket. It clumps into an intricate filamentary web of staggering complexity, a high entropy structure that would take an impossible amount of information to map perfectly. And dark energy, by relentlessly accelerating the expansion of the universe, is ensuring that the cosmos will eventually reach a state of maximum entropy, a cold, dark, evenly dispersed sea of particles where no more work can be done, often called the heat death of the universe. This end state is the ultimate high entropy configuration, and by its very nature, it would be the most information-rich state conceivable, because every particle's final, random position would be a unique data point in a frozen cosmic archive. This perspective completely flips the script on how we value the void. Its seeming emptiness and chaos are not signs of insignificance, but the very hallmarks of its incredible informational potential. The void is not a simple nothing. It is a complex, evolving system trending toward maximum information density. It could be the universe's ultimate hard drive, not in spite of its disorder, but because of it. The arrow of time, pushing the cosmos toward higher entropy, is simultaneously writing a more and more detailed story across the fabric of spacetime itself, a story whose finest print is written in the quantum fluctuations of the dark. While stars are the brilliant, low-entropy authors of their own localized tales, the void is the vast, high-entropy library that holds the complete and ever-expanding record of everything. But if we want the most direct, ancient evidence that the void is not empty but imprinted with a primordial story, we need to look back in time, all the way back to the very beginning. We need to tune our instruments to the oldest signal in the universe, a faint whisper of radiation that fills every cubic centimeter of space. This is the cosmic microwave background, or CMB, and it is perhaps the most profound example of information stored not in a star but in the void itself. Think of the CMB as the universe's baby picture, taken when it was just 380,000 years old. Before this moment, the cosmos was a searing, opaque plasma soup, so dense that light couldn't travel any meaningful distance before bouncing off a free electron. It was a chaotic, blinding fog, but as the universe expanded and cooled, a monumental event occurred. Electrons combined with protons to form the first neutral hydrogen atoms. Suddenly, the fog cleared. The photons, finally set free, began streaming across the universe in every direction. That first flash of light, once blazingly hot, has been stretched and cooled by the expanding universe over 13.8 billion years into a faint microwave static. And it is everywhere. If you turn on an old analog television to the snow between channels, about 1% of that static is this ancient afterglow, the echo of creation literally ringing in the emptiness. This background hiss is astonishingly uniform, varying by less than 1/1000th of a degree across the entire sky. but it is within those tiny, almost imperceptible fluctuations, those minute temperature variations, that the true information treasure is buried. These tiny ripples are not random noise, they are a cosmic fingerprint. They are a frozen snapshot of the density variations in the infant universe, the seeds from which all future structure would grow. Slightly denser patches, imprinted as slightly cooler spots in the CMB, would eventually collapse under their own gravity to form galaxies and clusters of galaxies. The less dense patches, the warmer spots, would become the great cosmic voids. The entire large-scale structure of the universe we see today, the glittering web of galaxies separated by vast dark empty regions, was literally blueprinted in these patterns over 13 billion years ago. Decoding this blueprint has been one of the greatest scientific endeavors of our time. Spacecraft like the COBE, WMAP, and most recently the Planck satellite have mapped these fluctuations with exquisite precision. By analyzing the statistical patterns of these hot and cold spots, cosmologists can read this fossil light like a cosmic Rosetta Stone. It tells us the precise age of the universe. It reveals the universe's total density and composition. How much is ordinary matter, how much is dark matter, and how much is dark energy. It even provides evidence for the period of inflationary expansion, a fraction of a second after the Big Bang, when the universe is thought to have expanded faster than the speed of light, planting the initial seeds for those very fluctuations. The informational richness of this signal is almost incomprehensible. The CMB is not localized to a point. It is a signal that permeates the entire observable universe. The void between stars is not just carrying this signal, it is the medium for this signal. Every direction we look, we are bathing in this data stream. The information content encoded in the precise patterns of the CMB is estimated to be around 10 to the power of 90 bits, a number so vast it dwarfs the information capacity of all the stars and planets in the observable universe combined. It is the ultimate historical archive, a data set that details the initial conditions of everything, and it is stored not in any luminous object, but in the apparent nothingness of space itself. This ancient light proves that the void has never been inert. It has always been an active, informative canvas, holding the deepest memories of the cosmos since the very first moments of time. Yet for all the ancient history written in the CMB, the void is not just a repository of the past. It is also a dynamic medium for carrying news of the most violent and dramatic events happening across the cosmos in near real time. It does this not through light or particles, but through ripples in the very fabric of reality itself. These are gravitational waves, and they represent one of the purest and most resilient forms of information ever discovered, traveling unimpeded through the absolute emptiness of intergalactic space. The story of gravitational waves begins with a prediction. Over a century ago, Albert Einstein, in his theory of general relativity, proposed that the universe's stage isn't a fixed, rigid thing. Instead, he described spacetime as a flexible, four-dimensional fabric, much like a taut rubber sheet. When massive objects like stars or black holes move through this fabric, they create ripples, warps, and waves that propagate outward at the speed of light. Einstein himself was skeptical we could ever detect something so faint, but in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, did just that. The signal it captured was from a pair of black holes, each about 30 times the mass of our Sun, locked in a final, fatal dance over 1 billion light-years away. In a fraction of a second, they spiraled into each other and merged, converting an amount of mass several times that of our Sun directly into energy, shaking the fabric of spacetime with a power that briefly outstripped all the stars in the observable universe combined. That tremor, after traveling for over 1 billion years, stretched and squeezed our planet by a distance 1,000th the width of a proton, and LIGO felt it. This was more than just a confirmation of Einstein's theory. It was the opening of an entirely new window on the universe. Astronomers had always relied on light, visible, radio, X-ray, to observe the cosmos. But light can be blocked. It can be absorbed by cosmic dust, scattered by gas clouds, or bent by gravity. Gravitational waves face no such obstacles. They are a pristine signal. They pass through planets, through stars, through entire galaxies without any distortion or loss of information. The void is not an obstacle for them. It is the perfect transmission medium. A gravitational wave generated by a cataclysm on the far side of the universe will arrive at our detectors with its information perfectly intact, telling a story that light simply cannot. And what a story it tells! When LIGO and its European counterpart, VIRGO, detect a wave, they are not just hearing a simple thump. They are reading a complex chirp, a rapidly rising frequency that encodes an incredible wealth of data. From that signal, astrophysicists can extract the masses of the objects that collided, their spins, their orbital dynamics in the final moments before merger, and even the precise distance to the event. It's like listening to a cosmic symphony where every note reveals a fundamental property of the performers. We have now heard the mergers of countless black holes and neutron stars, events that are often completely invisible to traditional telescopes. In one spectacular case, the merger of two neutron stars was seen by both gravitational wave observatories and light-based telescopes, a new field called multi-messenger astronomy that gave us a complete picture of an event that created heavy elements like gold and platinum and scattered them across the galaxy. This changes the informational calculus of the void completely. While a star broadcasts its information primarily through electromagnetic radiation, a form of energy that can be corrupted or lost on its long journey, gravitational waves are a direct, uncorrupted transmission through the substrate of spacetime. The void is not a passive container for these waves. It is the very strings that are being plucked. Every ripple is a data packet carrying news of the most extreme physics in the universe, from the crushing depths of neutron stars to the paradoxical edges of black hole event horizons. The information they carry is not about surface properties, but about the fundamental nature of gravity and mass itself. And unlike the light from a star, which eventually fades, the gravitational wave from a long-ago collision is still out there, traveling forever through the expanding void, a permanent ripple in the cosmic pond containing a perfect record of a monstrously powerful event. This eternal, flawless transmission through the emptiness makes the void an unparalleled galactic communication network, a medium whose informational capacity and fidelity may indeed surpass the brilliant but localized and fragile signals emanating from the stars. If stars represent the brilliant, information-rich beacons of the cosmos, and the quantum vacuum is the seething, data-dense substrate of spacetime, then black holes are the ultimate cosmic paradox. They are regions where gravity becomes so overwhelmingly powerful that not even light can escape their grasp. For decades, they were thought to be the universe's ultimate shredders, not just of matter and energy, but of information itself. This belief created one of the most profound conflicts in modern physics, a puzzle so deep it threatened to unravel our understanding of reality. This is the black hole information paradox, and its potential resolution doesn't just save physics, it points directly to the void as the universe's ultimate archive. The problem begins with a seemingly simple question: what happens to the information about an object when it falls into a black hole? Imagine you throw a book into a black hole. That book is made of specific atoms arranged in a specific order that encodes a story. According to Einstein's general relativity, the book would cross the event horizon, the point of no return, and be inexorably pulled toward the central singularity, where it would be crushed out of existence. From the perspective of the outside universe, every unique detail that made that book itself, the information, would be lost forever. It would be as if you had thrown the book into a cosmic incinerator, reducing its intricate information to nothing but a single number, the black hole's total mass, charge, and spin. This presented no immediate problem until Stephen Hawking applied quantum mechanics to black holes in the 1970s and made a shocking discovery. Hawking realized that due to quantum effects occurring just outside the event horizon, black holes aren't completely black. They should slowly emit a faint glow of particles, now known as Hawking radiation. This radiation allows a black hole to gradually lose mass and, over astronomical timescales, completely evaporate. But here's the catch. Hawking calculated that this radiation is purely thermal. It's random heat radiation, like the glow from a hot stove. It contains no information whatsoever about what fell into the black hole. So, when the black hole finally evaporates and vanishes, what happens to the information from that book? According to the bedrock principle of quantum mechanics, information can never be truly destroyed. It can be scrambled, but it must be preserved in some form. This is the paradox. Quantum mechanics says the information must be saved, but Hawking's calculation suggested it was irrevocably lost. For decades, physicists were split into two camps, with Hawking himself famously betting that information was indeed destroyed. The potential solution to this crisis doesn't just preserve information. It implicates the void in a breathtaking way. The key insight came from asking where the information might be stored. If it's not destroyed with the black hole, and it's not carried away by the Hawking radiation, then it must be encoded somewhere else. That somewhere is the event horizon itself. Building on the holographic principle we discussed earlier, theorists like Leonard Susskind and Gerard T. Hooft proposed that all the information about everything that falls into a black hole is not lost inside, but is instead smeared out and perfectly encoded on the two-dimensional surface of its event horizon. The three-dimensional interior is a projection. The horizon is the film. When Hawking radiation is emitted, it's not coming from deep within the hole. It's generated from the quantum vacuum fluctuations right at the edge of the horizon. As these particles are created, they can subtly interact with this encoded information on the surface. Over the incredibly long lifetime of the black hole's evaporation, this process could slowly and meticulously imprint the information about the fallen book onto the outgoing radiation. The information isn't lost, it's returned to the universe in a vastly transformed but complete state. This leads us to an even more radical idea, the black hole firewall paradox. If information is being released from the horizon, what does that mean for someone falling in? The principles of quantum mechanics suggest that for the information to be saved, the event horizon cannot be the smooth, uneventful space that Einstein predicted. Instead, it might be a searing wall of high-energy particles, a firewall, that would instantly incinerate anything crossing it. This presents a new paradox, forcing physicists to choose between the smoothness of spacetime promised by general relativity and the necessity of information conservation demanded by quantum mechanics. While the debate continues, it highlights the incredible tension around this concept and underscores the pivotal role of the horizon, the ultimate boundary between the black hole and the void. So, how does this all connect the destructive power of black holes to the informational richness of the void? The event horizon is not a wall separating the black hole from nothing. It is an interface where the black hole interacts with the external quantum vacuum. The Hawking radiation that carries the information away is born from the void itself, from those virtual particle pairs flickering in and out of existence. One particle falls in, allowing its partner to escape as radiation. The void is not passive in this process. It is the active medium through which the black hole communicates its stored data back to the universe. The information from every star, every planet, and every book that ever fell in is not destroyed. It is processed, translated, and ultimately emitted back into the cosmic void, encoded in the faint Hawking radiation that will permeate space long after the black hole itself is gone. In this incredible light, black holes are not the end of information. They are the universe's most extreme and efficient information processors. They take complex, localized information, compress it onto a two-dimensional surface, and then, through a painstakingly slow quantum dance with the vacuum, they broadcast it back into the cosmos. They don't destroy data, they redistribute it, scattering it across the void in the most subtle and fundamental way imaginable. The void becomes the recipient and the permanent repository for this information. Even the most terrifying objects in the universe, the ultimate symbols of cosmic oblivion, may in fact be contributors to the vast, invisible data reservoir that is the true foundation of reality. But if the idea of black holes slowly leaking information back into the void feels like a gradual, cosmic recycling program, then the concept we're about to explore is the exact opposite, a sudden, violent, and total cosmic reset. It's one of the most speculative yet terrifying ideas in all of theoretical physics, and it hinges on a startling possibility that the void we exist in, the very quantum vacuum that makes up our reality, might not be in its truest, most stable state. It could be a false vacuum, a cosmic accident waiting to correct itself in an event known as vacuum decay, and process that wouldn't just destroy everything, but would rewrite the very laws of physics and all the information they contain. To understand this, we need to think of the universe's vacuum state not as a single, static thing, but as a landscape of possibilities. Imagine a ball resting in a small valley on the side of a gigantic, rolling hill. The ball is stable where it is. It won't spontaneously roll away. This valley represents our current vacuum state. It's what we call a metastable state. It's stable for now, but it's not the lowest possible energy state it could be in. Now picture the base of the entire hill, a much deeper, broader valley far below. That represents the true vacuum, the absolute lowest energy state the universe could potentially achieve. The terrifying implication is that our universe's vacuum might be like that ball in the higher valley metastable. And if something were to knock it out of its comfortable dip, it would come crashing down into the true vacuum, releasing a colossal amount of energy in the process. How could such a transition happen? Through a quantum phenomenon known as tunneling. In the quantum world, particles can sometimes cheat, finding a way through an energy barrier they classically shouldn't be able to cross. It's as if that ball in the valley spontaneously teleported through the hill to the deeper valley below. In the case of the vacuum, a random quantum fluctuation in some tiny region of space could, by sheer unimaginably small probability, trigger this transition. It would create a microscopic bubble of true vacuum, and this bubble would be catastrophic. The laws of physics inside this bubble would be different. Fundamental constants like the strength of gravity or the mass of an electron could change. This new state would be more stable, and it would expand outward at nearly the speed of light, its boundary a wall of immense energy that would obliterate everything in its path, not by explosion, but by rewriting the rules of existence itself. One moment you're there, the next, the particles you're made of no longer interact in a way that allows for atoms, chemistry, or life. This isn't just about destruction, It's about information on the most fundamental level. The laws of physics themselves are a form of information. The specific value of the gravitational constant, the mass of a quark, the charge of an electron, these aren't arbitrary numbers. They are the fixed parameters that define our reality, the code upon which our universe runs. The fact that our vacuum state allows for these specific values is the ultimate data set. The false vacuum theory suggests that this code is not necessarily permanent. The void's true ground state, that deeper valley, holds a different set of rules, a different cosmic code. The latent potential for this transition means the void contains, in a sense, the blueprints for every possible version of reality. It is a repository of information not just about our universe, but about all possible universes that could exist under different physical laws. The informational potency here is absolute. A vacuum decay event would be the ultimate data wipe and reprogramming. It would erase all the information our universe has ever produced, every star, every planet, every thought, and replace it with a new, unknown dataset defined by the new physical constants of the true vacuum. It's a thought experiment that casts the void not just as a storage device, but as an active programmer with the potential to debug and reboot the entire system. While the probability of such an event occurring in any given region of space is infinitesimally small across billions of years, the mere possibility underscores a profound truth. The apparent stability of our reality is built on a foundation that may be provisional, and the deepest darkness holds the secrets to its own potential transformation. So far, we've explored how the void might store information through quantum foam, dark matter, and even holographic principles. But to truly put this idea to the test, we need a way to measure it. We need a set of cosmic scales to weigh the information content of a star against the information content of empty space. This is where we turn from the physical to the computational, applying the rigorous tools of modern information theory to the grandest stage of all, the entire universe. This isn't just about counting bits, it's about understanding the very nature of cosmic complexity. At its most fundamental, this approach asks a deceptively simple question: how much information is required to describe something perfectly? For a star, the process is complex but follows well-understood physical laws. We can describe its mass, its composition, its temperature, and its rate of fusion with a set of equations. While the number of variables is immense, the system is largely deterministic and ordered. You could, in principle, write a very complex computer program that simulates a star's life cycle. The amount of information in that program, its code length, gives us a sense of the star's algorithmic information content. It's a massive file, to be sure, but it is ultimately finite and bound by the rules of stellar physics. Now let's write a program to simulate a cubic light-year of the quantum vacuum. Where do we even begin? We must account for the spontaneous, probabilistic flickering of virtual particles, events that are not determined by prior causes but are fundamental uncertainties. We must model the invisible gravitational landscape of dark matter, a web of unimaginable complexity that we can only infer. We must include the smooth but relentless pressure of dark energy, a constant that itself might be a variable. The program needed to simulate this emptiness wouldn't be a straightforward set of equations. It would have to be a massive, open-ended simulation of probability and chaos. It would likely be vastly longer, more complex, and more computationally expensive than the program for the star. This suggests that the void possesses a higher degree of algorithmic complexity. Its description requires more information because its behavior is less compressible, less predictable, and more fundamentally random. This distinction highlights a crucial difference between two types of information. A star is a brilliant example of information throughput. It processes a staggering amount of data, converting hydrogen into helium and releasing photons in a continuous, luminous stream. But the void embodies information potential. It is not processing information in the same way. It is information encoded in its very structure. Its complexity isn't in its output, but in its state. Think of it like the difference between a powerful computer running a single, complicated calculation and the same computer's hardware at rest. The calculation is impressive, but the physical arrangement of the billions of transistors on the computer's chip, their precise configuration and connection, represents a deeper, more fundamental level of information that makes the calculation possible in the first place. The void may be the universe's motherboard, and the stars are just the programs running on it. This theoretical framework gives us a new lens through which to view the cosmos. It provides a mathematical language to quantify the seemingly unquantifiable, to compare the informational richness of the radiant and the dark. When we apply these scales, the narrative tilts decisively. The ordered fusion of a star, for all its glory, may be informationally simpler than the chaotic, probabilistic dance of the quantum vacuum. The void's superiority may not lie in the volume of data it broadcasts, but in the profound, incompressible complexity of its eternal, underlying state, a complexity that makes our reality possible. But if we shift our focus from the mechanics of information to the profound question of our own existence, we enter a realm where physics and philosophy converge in one of the most compelling ideas in modern cosmology, the anthropic principle. This principle confronts a staggering coincidence: the fact that the fundamental constants of our universe appear to be exquisitely fine-tuned for the emergence of life. The strength of gravity, the force of electromagnetism, the mass of a proton, if any of these values were altered by even a minuscule fraction, the universe as we know it would be impossible. Stars would not ignite, complex atoms would not form, and life could never arise. We find ourselves in a cosmos that seems perfectly calibrated for our existence, and this begs a monumental question: why? The answer, incredibly, might not be written in the stars but hidden within the informational depths of the void itself. This fine-tuning is not a minor adjustment, it is a series of cosmic miracles. For instance, if the strong nuclear force that binds atomic nuclei together were just a few % stronger, all the hydrogen in the early universe would have fused into helium and then into heavier elements almost instantly. There would be no long-lived stars like our Sun to provide stable energy for billions of years. If it were slightly weaker, hydrogen wouldn't fuse at all, and the universe would be a cold, dark expanse of simple atoms with no engines to power life. The cosmological constant, which governs the acceleration of the universe's expansion driven by dark energy, is fine-tuned to an accuracy of 1 part in 10 to the power of 120. That is a number so incomprehensibly precise it defies analogy. It is like throwing a dart from the edge of the observable universe and hitting a 1-millimeter target on Earth, blindfolded. This isn't just luck, it demands an explanation. The anthropic principle offers a framework for this explanation, essentially stating that we observe a universe compatible with our existence because, well, we are here to observe it. In a multiverse of countless universes, each with different physical constants and laws, we naturally find ourselves in one of the rare, habitable ones. But this merely reframes the question: where do these different universes and their laws come from? Their blueprints, their very potential for existence, may be encoded in the quantum information of the void. The same quantum fluctuations that create a seething foam of virtual particles could also, on a much grander scale, generate the seeds for entire bubble universes with slightly different physical parameters. In this view, our universe isn't a single, isolated experiment. It is one outcome in a vast landscape of possibilities, and the void is the fertile ground from which all these possibilities spring. This connects the void's information directly to the reason we are here. The quantum vacuum state isn't just empty. It has specific properties that determine the laws of physics within our cosmic bubble. The specific, low-energy state of our vacuum allows for the existence of stable matter and the four fundamental forces we know. A different vacuum state in another universe might have 5 forces, or gravity might be repulsive. The information that defines our particular vacuum, the very rules of our game, isn't stored in any star or galaxy. It is embedded in the fabric of spacetime itself, in the void. This makes the void not just an information repository, but the ultimate source code for reality. The stars are simply actors following a script written into the quantum fields of the dark. This leads to a deeply philosophical and personal reflection. If the information necessary for our existence is woven into the void, then our connection to the cosmos is more intimate and fundamental than we ever imagined. We are not just observers of the universe, we are manifestations of its deepest informational layers. The carbon in our bodies, the iron in our blood, was forged in the hearts of stars. That much is true. But the laws that allowed those stars to form, to live, and to die were imprinted into the quantum vacuum at the dawn of time. The void is not a cold, indifferent emptiness. It is the necessary precondition for everything we see and are. Its informational structure is the reason the universe is comprehensible, stable, and hospitable. In this light, the darkness between the stars is not a barren wasteland to be crossed, but the very foundation of our being, a canvas of potential upon which our entire story was painted. The mind-bending theories we've explored aren't just abstract curiosities for physicists. They point toward a future where humanity might not just observe the cosmos, but actively converse with it. The idea of harnessing the information saturating the void sounds like the premise of a science fiction epic, yet it's a frontier being seriously contemplated by some of our most visionary scientists and engineers. Imagine a technology that doesn't simply use space as a medium to travel through, but treats the fabric of spacetime itself as the most powerful processor and communication network ever conceived. The first step toward this future is developing the senses to perceive the void's subtle data stream. Today's gravitational wave observatories like LIGO are the primordial ancestors of this technology. These instruments are already listening to the ripples in spacetime, but they are massive, earth-bound, and incredibly sensitive to terrestrial interference. The next generation could involve quantum sensors of unimaginable precision. Think of a network of satellites in the quiet vacuum of space, each containing a cloud of atoms cooled to near absolute zero. In this ultra-sensitive state, the slightest tremor in spacetime, a passing gravitational wave, a fluctuation in the local quantum field, would disturb the atoms, and we could read that disturbance. This wouldn't just be about detecting colossal black hole mergers. It could allow us to map the gravitational landscape of dark matter filaments, or even tune into the faint, constant hiss of the quantum foam itself. We would, in effect, be building ears to hear the whispers of the universe. This leads to the extraordinary concept of a cosmic internet. Our current communications are limited by the speed of light and can be blocked or degraded by matter. But what if we could encode information directly onto spacetime itself? Gravitational waves travel at light speed, but are impervious to cosmic dust clouds or atmospheric interference. A civilization advanced enough could theoretically generate precise, targeted gravitational wave signals, perhaps by manipulating massive objects with incredible precision, to send messages across the galaxy that are perfectly clear and utterly undetectable to any technology not specifically listening for them. It would be the ultimate secure channel, a whisper in the fabric of reality that only those who understand the language of gravity could hear. Perhaps the most revolutionary and daunting application lies in energy and computation. The quantum vacuum isn't just full of information, it's brimming with zero-point energy. The challenge is that this energy is everywhere and nowhere at once, like trying to draw water from a perfectly level ocean. The energy difference between virtual particles popping in and out of existence is unimaginably small and fleeting. Harnessing it would be like trying to power a city by capturing the energy of individual raindrops in a storm. Yet the theoretical potential is staggering. If we could find a way to tap even a tiny, sustainable fraction of this vacuum energy, it would represent a clean, limitless power source, fundamentally ending our reliance on planetary resources. Similarly, the idea of vacuum energy computation pushes the boundaries of imagination. If every quantum fluctuation is a bit of data, then the universe is already performing an incalculable number of operations every second. A computer that could somehow orchestrate these fluctuations using the spontaneous creation and annihilation of particles to perform logic gates would be more powerful than every supercomputer on Earth combined. It wouldn't compute in space, it would use space itself as the computer. We wouldn't be building a processor and putting it in a box, we'd be learning to program the very void. Of course, the challenges are as profound as the potential. The signals we're talking about are incredibly faint, buried in a sea of quantum noise. Differentiating a meaningful signal from the background hum of reality will require technologies we can barely envision. The energy scales involved are either astronomically large or subatomically tiny, far beyond our current engineering capabilities, and ethically, the power to manipulate the fabric of spacetime itself comes with unimaginable responsibility. Tinkering with the vacuum state, as we discussed with vacuum decay, carries existential risks we are not yet equipped to understand, let alone manage. Yet the pursuit is worth it. The reward for learning to read the void's information isn't just faster phones or unlimited energy. It's a fundamental understanding of reality. It would be like discovering that the air we breathe is actually made of tiny, invisible words, and then learning how to read them. We could finally decode the full history of the universe directly from spacetime's memory, understand the true nature of dark matter and dark energy, and perhaps even find answers to questions we haven't yet learned how to ask. This isn't just about building new machines, it's about evolving into a species that is truly integrated with the cosmos, moving from passive inhabitants of space to active participants in the grand, informational dance of the universe. Long before telescopes and quantum theory, humanity gazed into the starry night and pondered the profound darkness between the lights. Our ancestors were not just storytellers, they were the first cosmologists, and their interpretations of the void reveal a deep, timeless fascination with the concept of nothingness. In the Western world, one of the most influential ideas came from the ancient Greek philosopher Aristotle, who put forth a principle known as horror vacui, nature's abhorrence of a vacuum. Aristotle argued that a true void, a completely empty space, was a logical impossibility. He believed nature would always rush in to fill any emptiness, that the universe was a plenum, a fullness where every space had to be occupied by some form of matter. This idea held sway for nearly 2,000 years, shaping a worldview where emptiness was seen as an error, a flaw in the cosmic order that needed to be corrected. It was a perspective that viewed the void with suspicion, as something to be avoided and filled. Meanwhile, in the East, philosophical traditions were developing a radically different and more nuanced relationship with the void. In Taoist philosophy, emptiness is not a lack but a vital principle of potential. The classic text, the Tao Te Ching, uses the metaphor of a vessel, a bowl, a room, a wheel to make this point. It is the empty space inside a pot that gives it its usefulness. It is the hollow hub of a wheel that allows the axle to turn. Here, emptiness is not a negative state but a receptive, creative one. It is the silent ground from which all activity springs. This concept found its most profound expression in Buddhist philosophy, particularly in the doctrine of sunyata, often translated as emptiness or voidness. This is not a nihilistic nothingness, but a realization that all things are empty of a separate, independent existence. Everything is interconnected, dependent on everything else, and ultimately grounded in a vast, open potentiality. The void, in this view, is the ultimate nature of reality, not a barren wasteland, but a fertile field of infinite possibility. This cultural dance with emptiness resonated through art and mythology for centuries. Medieval and Renaissance artists, influenced by the Christian worldview and Aristotelian thought, often filled every inch of their canvases and cathedrals with intricate detail, a visual manifestation of horror vacui, a fear of leaving any space barren and unadorned. Yet they also painted the night sky as a deep, black velvet backdrop that made the divine figures and stars above seem to glow with an otherworldly light, acknowledging the power of the dark to define the light. In mythology, the void frequently appears as the primordial state before creation. The ancient Egyptian cosmology began with Nun, a dark, watery abyss that existed before the gods and the world. The Norse creation myth starts in Ginnungagap, a great yawning void where the meeting of fire and ice sparked the first life. These stories didn't see the void as mere nothing. They recognized it as the silent, generative precursor to everything, the dark canvas awaiting the first brushstroke of existence. The scientific revolution began to radically reshape this ancient dialogue. In the 17th century, Evangelista Torricelli and Blaise Pascal conducted experiments with mercury and barometers, finally demonstrating that a vacuum could indeed be created and that it exerted pressure. Nature did not abhor a vacuum, it simply obeyed different physical laws. This was a monumental shift. The void was now a measurable, physical reality, not a philosophical error. This empirical conquest of emptiness reached its symbolic peak in 1969, when Apollo astronauts transmitted back an image of the Earth, a single, vibrant oasis of life and color, suspended in the overwhelming blackness of space. That photograph did more than just show us our planet. It showed us the void, and it was vaster and more absolute than any ancient myth had ever conceived. Yet, the most profound transformation in our understanding is happening right now, in our own time. Modern cosmology and quantum physics have not just confirmed the existence of the void, they have utterly reinvented it. We now know that the vacuum of space is not the passive, inert nothingness of Pascal's experiments or the cold, dead emptiness between stars in the Apollo photo. It is, as we have explored, a seething quantum foam, a dynamic plenum of virtual particles, dark energy, and gravitational waves. The science of the 20th and 21st centuries has effectively merged the Eastern and Western views. We have confirmed that the void is indeed a fullness, as Aristotle insisted, but not one of matter. It is a fullness of activity, of potential, of information. And we have also confirmed that it is the ground of all being, the generative source of everything, as Taoist and Buddhist philosophers intuited. Their emptiness as potential is our quantum field fluctuation. Their interconnected void is our cosmological constant and spacetime fabric. This long historical arc, from fearing the void to understanding its creative potential, shows that our curiosity about nothingness is a fundamental part of the human experience. Every culture, in its own way, has tried to decipher the darkness, and our scientific journey is simply the latest chapter in that timeless story. We have not replaced these ancient myths and philosophies. We have built upon them, using new tools to answer the same eternal questions. We once filled the void with gods and monsters to give it meaning. Now we probe it with satellites and particle accelerators, and in doing so, we are discovering that the truth is far more strange and wonderful than any myth. The void is not something to be feared or filled. It is the most dynamic and informative part of our universe, and we are only just beginning to learn its language. So how do we actually stack up the information content of a star against the sheer, overwhelming volume of the void? It's a monumental task, but by borrowing concepts from computer science and physics, we can attempt to build a set of cosmic scales. Let's start with the most straightforward metric, sheer physical volume. The numbers here are so lopsided they border on the absurd. Stars, for all their brilliance, are incredibly isolated. If you were to take all the stars in a typical galaxy and squish them together, they would occupy a tiny, tiny fraction of its total volume. Our own Milky Way is about 100,000 light-years across, but the combined volume of all its several hundred billion stars is less than a trillionth of the galaxy's total space. The rest is the void, the unimaginably vast emptiness between stars and the even vaster gulfs between galaxies. When you scale this up to the entire observable universe, the disparity becomes almost comical. Stars are mere specks of dust floating in a cathedral so immense we can barely conceive of it. So from a pure real estate perspective, the void wins by default. There's just so much more of it, but volume alone isn't the same as information density. A deserted beach is huge, but a single smartphone contains more information. So we have to ask what's happening inside that volume. This is where the concept of entropy becomes our most valuable tool, as it directly measures information content. A star is a fascinating paradox, a high-energy system with relatively low entropy. It's a massive, organized, and concentrated sphere of hot gas. Its internal processes, while turbulent, follow predictable laws of nuclear physics and hydrodynamics. You could describe its state with a set of complex but ultimately finite equations. The information it emits, its light spectrum, is rich but patterned. It's like a brilliantly complex but repetitive symphony. The total information it contains and broadcasts over its lifetime is immense, but it is ultimately bounded by its mass, its composition, and its lifespan. Now let's shrink our perspective down to a single cubic centimeter of the void. According to quantum field theory, this minuscule volume is a maelstrom of activity. Virtual particle pairs are flickering in and out of existence at an incredible rate. The electromagnetic field, the gravitational field, and other quantum fields are all fluctuating constantly. Each of these fluctuations is a probabilistic event, a decision between possible states. In information terms, each one is a bit, a 1 or a 0. The number of these events in just 1 cubic centimeter over just 1 second is astronomically huge. And this isn't a process with a beginning or end. It's eternal and happening everywhere at once. When you multiply this incomprehensible information density by the incomprehensible volume of the universe, the number of bits stored in the quantum vacuum becomes not just large, but truly infinite for all practical purposes, limited only by the finite age of the universe and the resolution of the Planck scale. This is the core of the void's advantage. Its information is not in large, obvious structures, but in an unimaginably fine-grained, ubiquitous mist of data. It's the difference between storing information on a few large, blazingly bright billboards, the stars, and storing it on quintillions of microscopic, invisible grains of sand that fill the entire cosmos. Even if each grain holds only a few bits, the cumulative total dwarfs the billboards. Physicists like Jacob Bekenstein and Stephen Hawking gave us a way to think about this limit with the Bekenstein bound, which states that the maximum amount of information that can be contained within any given region of space is proportional to the surface area of its boundary, not its volume. This holographic principle suggests that the information content of a region, whether it contains a star or just empty space, is ultimately limited by its surface. Since the void constitutes almost all of that surface area in the universe, it follows that it must also contain the lion's share of the information. Attempting to put actual numbers on this is, of course, fraught with difficulty and is a frontier of theoretical physics. Some rough estimates trying to calculate the information capacity of the universe based on the number of Planck scale volumes it contains arrive at figures around 10 to the power of 120 bits. The contribution from all the stars, planets, and galaxies is a vanishingly small fraction of this total. The rest is in the fabric of spacetime itself, in the quantum fields, the dark matter halos, the dark energy, and the gravitational wave background. The evidence, while indirect and theoretical, points overwhelmingly in one direction. The void's potential informational supremacy doesn't come from being loud and obvious like a star, but from being everywhere forever and fundamentally woven into the code of reality. The stars are the brilliant headlines. The void is the endless, microscopic print that contains the entire story. But if the idea of our universe's void containing unimaginable information feels vast, then the next concept we must explore is so expansive it redefines the word cosmos itself. We've been discussing the void as the space between stars and galaxies, but what if our entire universe, with all its hundreds of billions of galaxies, is itself just a single bubble floating in a much grander, perhaps infinite, cosmic ocean? This is the Multiverse Hypothesis, and it suggests that the informational richness of the void might not be confined to our reality alone, but could be a cross-dimensional network, a multiversal internet where data is shared between entirely separate universes, each with their own unique laws of physics. The most scientifically grounded version of this idea comes from the theory of eternal inflation. Imagine the aftermath of the Big Bang not as a single, smooth expansion, but as an endlessly bubbling cauldron of spacetime. In this model, the repulsive force that drove the initial inflation never completely turns off. Instead, the expanding universe acts like a rising loaf of raisin bread, but where the dough itself is constantly generating new dough. In this cosmic kitchen, our entire observable universe is just one raisin. Other raisins, other bubble universes, are constantly inflating into existence elsewhere in the meta-universe or the multiverse. Crucially, the physical laws inside each bubble are determined by the specific way its local vacuum state settled, a process known as symmetry breaking. One bubble might have a vacuum that produces strong nuclear forces, allowing for stars and planets. The bubble right next door might have a vacuum where electromagnetism is too weak for atoms to even form, creating a universe that is utterly dark and barren. In this view, the void isn't just the space within our universe. It is also the incomprehensibly vast space between these bubble universes, a meta-void that might make our own cosmic emptiness seem cluttered by comparison. This raises a staggering possibility. Could information somehow bridge the gap between these isolated realities? The laws of physics as we know them are locked within our bubble. Light and matter cannot cross the inflationary boundary separating us from another universe. But there are more subtle quantum concepts that suggest a leak might be possible. One intriguing candidate is quantum entanglement, that spooky action at a distance that Einstein famously disliked. When two particles become entangled, their properties are linked instantaneously, no matter how far apart they are separated. Some physicists, like Brian Greene, have speculated that particles could potentially become entangled across the boundary between bubble universes. If that were true, then a change to a particle in our universe could instantly influence its entangled partner in another universe, creating a flawless, instantaneous communication channel that bypasses the normal limits of spacetime. It would be a perfect transfer of information, a single bit of data shared between two realities that are otherwise completely sealed off from one another. Another theoretical pathway for cross-universal data exchange could be through spacetime tunnels known as Einstein-Rosen bridges, or wormholes. While stable, traversable wormholes are purely speculative and would require exotic matter to keep them open, they are mathematically possible within the framework of general relativity. If such a structure could somehow form, it wouldn't just connect two distant points within our universe. It could, in theory, connect two separate universes entirely. Information, whether in the form of particles, fields, or even just quantum states, could flow through this tunnel, allowing for a direct exchange of data between cosmic bubbles. The void within the wormhole itself would act as the conduit, the cosmic fiber optic cable, linking two entirely different sets of physical laws. The implications for the void's information capacity are quite literally infinite. If our universe's vacuum can store information in its quantum foam, then the meta-void between bubble universes represents a storage medium of an entirely higher order. Furthermore, if information can be shared or compared across universes, then the void becomes a comparative database. It wouldn't just hold the data for our reality. It could hold a library of every possible variation of physical law, a multiversal archive detailing every way a universe could possibly exist. The information content of any single star, or even all stars in one universe, becomes an insignificant entry in an infinite catalog. The true cosmic library isn't housed in the galaxies. It's in the gaps between the worlds, in the multidimensional void that hosts the totality of existence. This transforms the void from a passive container into an active, relational network, the fundamental substrate connecting all realities and making the sum total of cosmic information not just vast but truly unbounded. But as we stand on the precipice of potentially learning to read this cosmic library, we are forced to confront a series of profound and unsettling questions that reach far beyond the realm of physics. If the void is indeed a reservoir of information, perhaps containing the entire history of the cosmos, the blueprints for reality, or even data about our own lives, then who does that information belong to? The very act of observation might be more than just a passive reading. It could be an interaction that changes the data itself. This moves us from the how of cosmic information into the deeply complex territories of ethics and philosophy, challenging us to consider our role and our responsibilities in an information-saturated universe. Imagine a future where our technology has advanced to the point where we can not only detect the faintest gravitational wave echoes of ancient events, but can decode them with such precision that we could reconstruct the specific history of a distant planet. What if we could observe the rise and fall of a civilization a billion light-years away, learning their secrets, their art, and their tragedies, all from the ripples in space-time they left behind? This raises a fundamental question of cosmic privacy. Would that information be ours to access simply because we have the technological capability to do so? Does a civilization, even long extinct, have a right to its own historical privacy? Or does all information in the cosmos become a universal commons, free for any advanced species to uncover? This isn't just a question for science fiction. It forces us to define the ethical boundaries of curiosity itself, questioning whether the ability to know something always grants the right to know it. The ethical dilemmas become even more acute when we consider the potential for manipulation, not just observation. We've discussed the theoretical, albeit terrifying, concept of vacuum decay, the idea that a high-energy event could trigger a phase transition in the quantum vacuum, rewriting the laws of physics in its wake. While the probability is infinitesimally small, the mere possibility that an advanced experiment could inadvertently alter the fundamental constants of the universe is a responsibility of staggering magnitude. It would be the ultimate ecological disaster, not on a planetary scale but on a cosmic one. This places a profound ethical burden on the shoulders of scientists and, by extension, all of humanity. The pursuit of knowledge is a noble drive, but it must be tempered with a deep humility and a precautionary principle that recognizes that some doors, once opened, might not be able to be closed. The information in the void may be there for the reading, but that doesn't mean we should ever attempt to rewrite it. This leads us into even deeper philosophical waters concerning the nature of the information itself. Is the data in the quantum foam simply a passive record, a cosmic fossil waiting to be read, or could it have a more active role, perhaps even a form of agency? Some interpretations of quantum mechanics, like the participatory anthropic principle, suggest that the act of observation itself is what crystallizes reality from a cloud of probabilities. In this view, the information in the void isn't fixed until a conscious observer interacts with it. This would mean that consciousness isn't a mere byproduct of the universe, but an integral participant in its ongoing creation. The information isn't just out there, it's waiting for us to bring it into being, making us not just readers of the cosmic story, but co-authors. This blurs the line between discovering destiny and creating it, challenging our very notions of free will. Are our choices truly our own, or are they simply the reading of a script that was written into the quantum fields at the dawn of time? Ultimately, these questions converge on a single, humbling point: our place in the cosmos. For centuries, we have seen ourselves as separate from the universe, tiny observers on a small rock, looking out at a vast external reality. But if the void is suffused with information, and if we are made of the same quantum stuff as the void, then the separation is an illusion. We are not just in the universe is in us. The atoms in our bodies were forged in stars, and the laws that govern our thoughts are written into the vacuum of space. This realization fosters a powerful sense of connection and responsibility. We are the universe becomes self-aware, beginning to understand its own hidden language. This isn't a call to shrink from exploration, but to approach it with a new reverence, to see the quest for knowledge not as a conquest, but as a form of communion with the deepest layers of existence. The void may hold more information than the stars, but it is a shared inheritance, and with the power to access it comes the profound duty to do so with wisdom, wonder, and a deep respect for the sacred mystery of it all. Right now, in laboratories deep underground and with telescopes orbiting high above Earth, we are not just pondering these mysteries, we are actively hunting for the answers. The theoretical ideas about the void's hidden information are being put to the test by a new generation of experiments and observatories so advanced, they border on the magical. This isn't science fiction, this is the cutting edge of cosmology, where we are building the tools to finally listen to the whispers of the dark. One of the most direct ways to probe the quantum vacuum is not in space, but in highly controlled experiments on Earth. Scientists are using powerful lasers and supercooled mirrors to try and detect the faintest possible effects of quantum fluctuations. In labs across the world, researchers are attempting to measure the Casimir force with even greater precision, or to observe the subtle ways virtual particles might influence the behavior of atoms. Some are even trying to see if they can stimulate the vacuum, perhaps coaxing virtual particles into becoming real ones for a fleeting moment, a process that would give us a direct window into the seething energy of empty space. These experiments are incredibly difficult because they are fighting against a constant background of noise, thermal vibrations, seismic rumbles, even the passage of trucks on a distant highway. But by isolating their equipment and cooling it to near absolute zero, they are inching closer to isolating the pure signal of the void itself. To hunt for the invisible informants of dark matter, physicists have gone deep underground. In places like the Sanford Underground Research Facility in South Dakota, home to the LZ experiment, or Italy's Gran Sasso Laboratory, detectors are shielded by thousands of feet of rock from the constant rain of cosmic rays that bombard the Earth's surface. These experiments, often using vats of ultra-pure liquid xenon, wait in the profound silence and darkness for the once-in-a-lifetime event, a tiny bump, a flash of light, the telltale sign that a dark matter particle has finally struck an atom of normal matter. While a definitive, direct detection remains elusive, each experiment that comes up empty helps to rule out whole classes of potential dark matter particles, narrowing the search and guiding theorists toward new ideas. It's a painstaking process of elimination, a cosmic detective story unfolding in the quiet darkness beneath our feet. Meanwhile, in the silent expanse of space, our robotic eyes are gathering light from the dawn of time. The James Webb Space Telescope is perhaps the most powerful tool ever built for looking into the void. Its infrared gaze can peer through cosmic dust to see the first galaxies forming, but it is also exquisitely sensitive to the faint thermal signatures of exoplanets. By studying the atmospheres of these distant worlds, Webb is indirectly probing the fundamental constants of the universe. Are the laws of physics the same there as they are here? Any slight variation could provide a crucial clue that our vacuum state is not unique, supporting multiverse theories and hinting that the void's informational code might be different in other corners of existence. It's not just a camera, it's a philosopher's stone transforming distant light into profound questions about reality itself. And we are not just looking, we are listening. The gravitational wave observatories LIGO, Virgo, and now Japan's Kagra have opened an entirely new sense. With each new detection of a black hole or neutron star merger, they are building a catalog of cosmic crashes. But the next generation of these instruments, like the planned Laser Interferometer Space Antenna, or LISA, will be a fleet of satellites flying in a perfect triangle millions of kilometers apart. Free from the seismic noise of Earth, LISA will be sensitive to gravitational waves of a much lower frequency, allowing it to hear the mergers of supermassive black holes at the hearts of galaxies, and possibly even the faint rumble from the inflationary epoch itself, a signal that would be a direct recording of the birth of the cosmos. This would be the ultimate act of cosmic archaeology, digging back to the very first moments when the void's informational structure was first laid down. These efforts are complemented by increasingly precise maps of the cosmic microwave background. The Planck satellite gave us our most detailed baby picture of the universe, but future missions propose to study its polarization, the specific direction of its light waves, with even greater accuracy. Tiny patterns in this polarization, known as B-modes, could contain the faint imprint of gravitational waves from the universe's first second, a smoking gun for the theory of cosmic inflation, and a direct measurement of the energy scales at which the vacuum first ignited the expansion of everything. It is the painstaking work of measuring impossibly small signals, but the reward is nothing less than a glimpse of creation. What's truly inspiring is that this isn't the work of a single genius in a lonely lab. It is a global, collaborative effort, a symphony of human curiosity conducted across continents and disciplines. Theoretical physicists develop the models that predict what we should look for. Engineers design and build machines of impossible sensitivity. Technicians and programmers maintain them and sift through petabytes of data. Each null result, each faint signal, each new piece of data is a collective step forward. We are, as a species, slowly assembling the key to decipher the universe's deepest code, and every day our technology becomes a little better, our methods a little sharper, and our understanding a little clearer. The void has kept its secrets for 13.8 billion years, but for the first time we are developing the tools and the intellect to finally begin reading them. But this journey into the quantum vacuum and the cosmic information it might hold leads us to a question that is perhaps the most perplexing of all, one that sits at the blurry intersection of physics and philosophy. We've been exploring the void as if it's an objective reality, a thing that exists independently, waiting for us to discover its secrets. But what if that's not the whole story? What if the very act of us looking, of us observing, somehow plays a role in making that information real in the first place? This brings us to the deeply mysterious role of consciousness itself, and whether the universe's hidden data requires a mind to bring it into focus. This idea isn't New Age speculation. It's rooted in one of the most fundamental and bizarre puzzles in quantum mechanics, something every physics student grapples with, the measurement problem. At the tiny scale of atoms and particles, things don't behave like billiard balls. Instead, they exist in a fuzzy cloud of possibilities called a wave function. An electron isn't in one place or another. It has a probability of being in many places at once, a superposition of states. The truly strange part is what happens when we try to measure it. The moment we look, the moment we set up a detector to see where that electron is, this cloud of possibilities seems to instantly collapse into a single, definite reality. The electron is suddenly right there, but what exactly constitutes a measurement? Is it the physical interaction with a detector, or does it require something more, a conscious awareness of the result? This is the heart of the famous Copenhagen interpretation, championed by figures like Niels Bohr and Werner Heisenberg. In this view, the wave function isn't just a description of what we don't know. It's a description of what isn't real until measured. Reality, at its most fundamental level, is probabilistic and becomes concrete only through the act of observation. The implication is staggering. The observer is inextricably linked to the system being observed. The universe doesn't have a single, predetermined history until it is witnessed. Now, extend this idea from a single electron in a lab to the vast quantum foam of the vacuum. Are the virtual particles popping in and out of existence doing so independently, or does their very flickering into a semi-real state depend on some form of universal observation? Is the void's informational tapestry being woven by the very act of us looking at it? A more radical extension of this idea is the participatory anthropic principle proposed by the brilliant physicist John Archibald Wheeler. He took the Copenhagen interpretation to its cosmic conclusion, suggesting that we are not just passive observers of a universe that exists out there, but active participants in bringing it into being. He used a powerful metaphor he called the delayed choice experiment. Imagine a particle of light, a photon, that has been traveling from a distant quasar for billions of years. On its way, it must pass by a massive galaxy whose gravity bends spacetime, acting like a lens and giving the photon two possible paths to reach us. We can choose, at the very last second after the photon has already journeyed for eons, how to set up our telescope to detect it. One setup will force the photon to reveal which path it took, behaving like a particle. Another setup will allow it to reveal that it took both paths simultaneously, interfering with itself like a wave. Our choice today, billions of years after the photon began its journey, seems to determine its past behavior. Wheeler's breathtaking suggestion was that we, through the act of observation, retroactively give that photon a definite history. We are participants in creating the past. Apply this to the void and the information it contains about the early universe. The patterns in the CMB, the echoes of inflation, might not be a fixed record. It might be a story that is only finalized now because we are here to read it. This forces us to confront the nature of information itself in the most profound way. Does information exist out there in the void as an objective property, waiting to be discovered like a fossil buried in rock? Or is information, in a truly fundamental sense, a relationship, a transaction that only completes itself when it is received and interpreted by a conscious mind? If a tree falls in a forest and no one is around to hear it, does it make a sound? The quantum version of that question is far deeper. If a quantum fluctuation occurs in the void and no one observes it, did it really happen in a definite way? The answers we lean toward are not just scientific, they are deeply philosophical. They shape our understanding of whether reality is something that exists independently of us, or whether consciousness is a fundamental force in the cosmos, a necessary ingredient for the universe to manifest itself from a sea of pure potential. The void may hold the information, but it might take a mind to collapse the wave function of possibility into the concrete data of experience, making the search for cosmic knowledge not just a journey outward, but a journey inward into the very nature of perception and being. To move from these mind-expanding concepts to something we can actually calculate, we need to turn to the universal language of precision and prediction, mathematics. While the ideas of a holographic universe or a seething quantum foam can feel abstract and philosophical, mathematicians and physicists have been hard at work developing rigorous frameworks to quantify these very notions, to put hard numbers on the seemingly ethereal idea of information in the void. These aren't just esoteric equations confined to chalkboards. They are the tools that allow us to build scales for weighing the information content of a star against the boundless potential of empty space. One of the most pivotal concepts in this endeavor is the Bekenstein bound, named after the physicist Jacob Bekenstein. This is a profound theoretical limit that tells us the maximum amount of information that can possibly be contained within any given region of space. What's truly counterintuitive is that this maximum isn't determined by the volume of the region, as common sense might suggest. You might think a bigger box could hold more information, just like a bigger hard drive. But the Bekenstein bound states that the ultimate information capacity is actually governed by the surface area of the region's boundary. It's directly proportional to the area, not the volume. This is a radical departure from how we normally think, and it emerges directly from the thermodynamics of black holes and the holographic principle. In simple terms, it suggests that all the information needed to perfectly describe everything inside a spherical region of space, every atom, every star, every person, could be encoded on the two-dimensional surface of that sphere, like a cosmic QR code. This mathematical result provides a powerful ceiling. It tells us that no matter what's inside a volume of space, whether it's a brilliant star or a perfect vacuum, the information it contains cannot exceed this fundamental limit defined by its surface area. To understand how we actually count information, we must return to the work of Claude Shannon and his concept of entropy, which, as we've discussed, is mathematically identical to information. In cosmology, we often deal with the entropy of a system. A star, for instance, has a certain amount of entropy, which is a measure of its internal disorder and, by extension, its information content. We can calculate a star's entropy based on its mass, temperature, and composition. A typical star like our Sun has an entropy on the order of 10 to the power of 58 in natural units. This is an astronomically large number, but it is finite. Now, let's apply the Bekenstein bound to a region of empty space the same size as our Sun. The maximum information that region could hold is also a finite number determined by its surface area. The fascinating result is that the entropy or information capacity of the empty space is many, many orders of magnitude larger than the entropy of the star itself. The void's potential, its maximum allowed data storage, dwarfs what the star actually contains. The star is not even coming close to filling its allotted informational real estate. But this is just the capacity for a single region. To grasp the void's true advantage, we must appreciate its sheer scale. Let's perform a thought experiment using another mathematical tool, integration. Imagine we want to compare the total information of all the stars in the observable universe to the total information capacity of all the space between them. First, we'd estimate the number of stars, which is around 10 to the power of 24. Multiply that by the average entropy per star, and you get a colossal number for the total stellar information. Now, for the void, we take the volume of the observable universe and divide it into tiny cubes, each at the Planck scale, the smallest possible unit of length. The number of these Planck volumes is around 10 to the power of 120. If each one can hold even a single bit of information due to quantum uncertainty, the total information capacity of the void becomes 10 to the power of 120 bits. When you compare these two totals, the number for the void is so vastly larger that the information from all the stars is a completely insignificant rounding error. A single drop in an ocean that is itself larger than all the oceans on every planet in the universe. These mathematical frameworks are powerful, but they are not without their limitations and open questions. The calculations often rely on simplifications, like treating the universe as a smooth, uniform box, which we know it is not on smaller scales. The precise relationship between quantum information, gravity, and spacetime is the holy grail of modern physics, and a complete theory of quantum gravity might one day revise these numbers. Furthermore, the Bekenstein bound applies to a region with a fixed boundary, but our universe is expanding, making the total information content a moving target. These are active areas of research, with physicists debating the nuances and interpretations. Yet, even with these caveats, the math paints a consistent and compelling picture. It provides the rigorous backbone for the incredible speculation, demonstrating through logic and calculation that the darkness is not empty. It is, by the very laws of physics, the most information-rich resource in the cosmos, a reservoir of potential data whose limits are set not by the matter within it, but by the fundamental architecture of reality itself. Of all the ideas we've explored, perhaps the most stubborn obstacle to understanding the void isn't its complexity, but a simple, deeply ingrained myth, the belief that empty space is truly empty. We intuitively picture a perfect, absolute nothingness, a pure black canvas waiting for something to be painted on it. This is our first and most fundamental misconception to dismantle. The reality, as modern physics has shown us, is that the vacuum of space is not a void in the sense of an absence. It is a presence. It is a dynamic, seething arena, more like an invisible ocean with powerful, hidden currents than a dry, barren seabed. To call it nothing is to fundamentally mislabel the most abundant something in the entire universe. This isn't just a semantic difference, it's the key that unlocks our entire discussion. If we cling to the idea of true emptiness, then the notion that it could hold more information than a star becomes logically impossible. But once we accept that the void is a physical entity with properties and activity, the door swings wide open to these extraordinary possibilities. Another common misunderstanding is our very definition of information itself. When we hear the word, we instinctively think of things we can directly perceive or record. Written words in a book, bits on a hard drive, or the light waves carrying data from a star. We imagine information must be tangible and structured, something with a clear beginning and end. This leads to the reasonable but incorrect conclusion that a brilliant, organized star must be a richer information source than a seemingly chaotic and dark void. But in a cosmic sense, information is something far more fundamental. It is not about meaning, it's about the number of possible states a system can be in. A perfectly ordered system, like a neat stack of papers, has low information content because it's easy to describe. A randomly shuffled stack has high information content because you need a long, specific list to describe its exact disordered state. The quantum void is the ultimate shuffled stack. Its information isn't in a structured message like a star's light spectrum. It's in the near infinite number of random, probabilistic states of its quantum fields. The information is not broadcast, it is embedded in the very fabric of reality, a fine-grained, ubiquitous data mist that fills all of space. Let's tackle the quantum foam, a term that can sound like scientific poetry rather than a real phenomenon. The misconception is that these virtual particles are just a mathematical quirk, not something physically real. The truth is, their effects are not only real but measurable. A helpful metaphor is to think of the vacuum as the surface of a hyperactive pond on a windy day. From a distance, the surface might look still and calm. But if you look closely, you see it's covered in tiny bubbles that constantly form and pop. These bubbles are the virtual particles. You can't capture a single bubble to study it, it pops too quickly. But you can absolutely measure the overall effect of all that bubbling activity. The Casimir effect, where two plates are pushed together in a vacuum, is like placing two floating corks on that pond. The ceaseless popping of bubbles between them creates less pressure than the bubbling activity on their outer sides, gently pushing them together. This proves the activity is not just theoretical, it exerts a real physical force. The quantum foam isn't an abstraction, it's the textured, energetic nature of spacetime itself. Then there's dark energy, perhaps the most mischaracterized concept in all of cosmology. It is often described as a force that is pushing the universe apart, which conjures images of some kind of cosmic wind or anti-gravity field. This is misleading. A more accurate, though still simplified, way to think about dark energy is as a property of empty space itself. Imagine you have a magical, stretchy fabric that has a built-in tendency to expand. The more of this fabric you have, the stronger the expansion becomes. Now, as the universe expands after the Big Bang, it creates more space. And because dark energy is a property of space itself, more space means more dark energy, which causes the expansion to accelerate further. It's not that something is actively pushing from the outside. It's that the very stage upon which the universe plays out is inherently expansive. The energy isn't dark because it's evil or sinister. It's dark simply because we cannot see it or directly detect it with our instruments. We only know it's there by its dramatic effect on the cosmos's expansion rate. It's not a force against gravity, it's a fundamental characteristic of the vacuum, woven into its invisible architecture. By clearing away these misconceptions, we replace a cartoonish picture of the cosmos with one that is far stranger and more magnificent. The void is not a sterile absence, but a vibrant and active participant in the universe's story. Its information is not in the form of legible words, but in the countless configurations of its quantum state. Understanding this is crucial because it shifts the void from a backdrop to a main character. It moves us from wondering if the darkness could hold information to asking how it does so, and on what unimaginable scale. This accurate foundation is what allows us to seriously entertain the incredible idea that the space between stars might be the universe's ultimate library, its most enduring and information-dense medium. Looking ahead, the next few decades promise to transform our understanding of the void from theoretical speculation into observable science, driven by a new generation of technologies that will let us not just infer, but directly interact with the fabric of spacetime itself. One of the most tantalizing goals on the horizon is the direct detection of vacuum fluctuations. Right now, we see their effects like the Casimir force, but actually measuring the fleeting existence of a virtual particle pair is like trying to photograph a single raindrop in a hurricane. However, projects like the Casimir effect experiments using superconducting quantum interference devices, or SQUID, are inching toward that goal. These incredibly sensitive instruments, operating at temperatures near absolute zero, might soon be able to detect the infinitesimal pressure changes and energy shifts caused by individual quantum events in a vacuum. Success here wouldn't just be a technical triumph. It would be like developing a microscope for reality itself, allowing us to watch the quantum foam fizzing in real time and finally providing direct, incontrovertible proof that empty space is a maelstrom of creative activity. Parallel to this, the hunt for experimental proof of the holographic principle is accelerating. The principle suggests a profound disconnect between our experienced reality and its true nature, and verifying it would be one of the most significant discoveries in the history of science. How could we possibly test such a radical idea? One approach involves studying the cosmic microwave background with even greater precision. The patterns imprinted on this ancient light during the universe's infancy might contain subtle statistical anomalies, a kind of pixelation or noise that could only be explained if our three-dimensional universe is indeed a projection from a two-dimensional boundary. Another frontier is using quantum computers to simulate holographic universes. By encoding the laws of physics onto a lower-dimensional network of qubits and watching how a three-dimensional reality emerges from their interactions, we could create a working, testable model of holography in the lab. These aren't just thought experiments, they are concrete research programs that could, within our lifetimes, show us that the universe is fundamentally a cosmic projection, and the void is the screen. The ultimate prize, the theory of everything that unites quantum mechanics with general relativity, also lies within the void's domain. For decades, string theory and loop quantum gravity have been the leading contenders, but both have struggled to make testable predictions. The key to breaking this deadlock may come from the void itself. The next great theoretical breakthrough might be a model where gravity isn't a fundamental force, but an emergent property, a side effect of the entropy and information stored on the holographic surface of a region of space. This idea, known as the entropic gravity hypothesis, suggests that what we feel as gravity is actually a statistical tendency for information to be maximized, much like how heat flows from hot to cold. If future experiments, perhaps measuring gravity at microscopic scales, find discrepancies with Newton's or Einstein's laws, It could be the first clue that gravity is indeed emergent, born from the informational dynamics of the quantum vacuum. Such a discovery would completely rewrite physics, placing the information content of the void at the very heart of our understanding of force and motion. This revolution won't be confined to theory. It will redefine our entire cosmological model. For centuries, our map of the universe has been a map of things: stars, galaxies, clusters. The next generation of maps will be a map of information. Missions like the European Space Agency's planned Laser Interferometer Space Antenna, or LISA, will chart the gravitational wave background of the universe, creating a dynamic soundtrack to cosmic history written in the vibrations of spacetime. The Nancy Grace Roman Space Telescope will map the distribution of dark matter in unprecedented detail, not by seeing it, but by tracing its gravitational influence on the void. These projects will produce datasets where the primary characters aren't luminous objects, but the invisible informational structures of dark matter halos, the quantum texture of empty space, and the ripples of primordial gravitational waves. We will stop seeing the universe as a collection of islands in an empty sea and start seeing it as a single, interconnected informational entity, where the voids are the hard drive and the galaxies are merely the processed data. The long-term implications stretch even beyond profound knowledge into the realm of transformative technology. While harnessing vacuum energy for power remains a formidable challenge, the principles of quantum information suggest other avenues. We might develop quantum communication systems that use entangled particles not just to send secure messages, but to transmit information through the vacuum itself, using the fabric of spacetime as the medium. Or we might learn to engineer metamaterials that can manipulate virtual particles, creating shields or lenses that bend reality in ways that seem like magic to us now. The ultimate far future dream is a technology that doesn't just use the void's information, but interfaces with it directly, a kind of cosmic internet router that taps into the holographic data layer of the universe itself. While this sounds like the stuff of science fiction, it is a logical extension of the principles we are beginning to uncover. The journey to understand the void is more than a quest for knowledge. It is the first step toward a future where humanity graduates from being inhabitants of the universe to becoming active participants in its deepest, most fundamental processes, learning to read and perhaps one day even to write in the language of reality itself. But the journey into the void doesn't have to end when this video does. This isn't just a story to watch, it's a mystery you can actually help solve. You don't need a billion-dollar telescope or a PhD in quantum physics to be a part of this cosmic exploration. Thanks to the internet and the collaborative spirit of modern science, there are incredible ways for anyone with curiosity and an internet connection to get directly involved in probing the universe's deepest secrets. One of the most rewarding paths is through citizen science projects. These are real research initiatives where scientists need the human brain's incredible pattern recognition, skills to analyze data that computers still struggle with. A fantastic place to start is with the Zooniverse platform. Right now, you could be helping cosmologists map the distribution of dark matter by looking at images of distant galaxies and noting how their light is warped by gravitational lensing in a project like Dark Energy Explorers. You're not just playing a game, you're contributing to real datasets that professional astronomers use to refine their models of the universe's invisible scaffolding. It's a direct line from your laptop to the frontiers of cosmology, allowing you to become an active participant in the discovery process. If you're fascinated by the raw data itself, you can go even deeper. Major observatories and space missions often make their data public. You can download actual images from the Hubble Space Telescope archive or delve into the cosmic microwave background data from the Planck satellite mission. While analyzing it requires some learning, there are free online tools and tutorials designed for amateur enthusiasts. Imagine looking at the same faint temperature fluctuations in the CMB that scientists used to understand the Big Bang, or inspecting the light curve of a distant supernova. You're not just learning about the void, you're handling its fingerprints. For a more structured understanding, the world of online learning is an endless resource. Platforms like Coursera and edX offer incredible courses on cosmology and astrophysics from top universities like Yale, Caltech, and the University of Edinburgh. You can take a deep dive into the evolving universe or explore the greatest unsolved mysteries of the universe, with leading experts guiding you every step of the way. Many of these courses are free to audit, putting a world-class education right at your fingertips. If you prefer books, works like The Black Hole War by Leonard Susskind or The Fabric of the Cosmos by Brian Greene offer thrilling and accessible narratives that unpack the very concepts we've been discussing, from holography to the nature of spacetime. And of course, the conversation can continue right here. The comment section below is more than just a place for feedback. It's a digital town square for everyone fascinated by these ideas. What part of this exploration into the void resonated most with you? Was it the holographic principle, the potential of vacuum energy, or the sheer scale of the dark cosmos? Do you have a different perspective or a burning question that this video sparked? Share your thoughts. Some of the most fascinating insights often come from these discussions, where a curious mind will pose a question that makes everyone see something in a completely new light. This is how we build a community of cosmic explorers, learning from each other as we try to piece together the grand puzzle of existence. Your curiosity is the most important tool in this investigation, and it's a journey we can take together. To make these grand theories feel tangible, let's turn our gaze to a specific, real-world place on the cosmic map, a place where the void isn't just a concept, but a stunning, almost unsettling reality. This is the Boötes Void, one of the largest known structures in the entire observable universe, and it is so profoundly empty that it has earned the nickname the Great Nothing. Discovered in the 1980s by astronomers Robert Kirshner and his colleagues, the Boötes Void is a spherical region of space, roughly 700 million light-years across, that contains almost nothing. To put that staggering scale into perspective, if you placed our Milky Way galaxy at the center of this void, the next nearest galaxy would be so far away that its light would take millions of years to reach us. In a region of space large enough to contain tens of thousands of galaxies, astronomers have found only about 60. The rest is an expanse of darkness so vast it challenges our very understanding of how the universe is structured. So what does this colossal absence, this great cosmic desert, tell us about information? At first glance, it seems to represent the ultimate example of low information density. If information is tied to matter and energy, then the Boötes Void should be an informational wasteland. But this is where our new perspective turns that assumption on its head. The profound emptiness of the Boötes Void isn't a blank spot on the map. It's a critical data point in the cosmic web. Its existence and its startling scarcity of galaxies are not an error or an accident. They are a direct consequence of the initial conditions of the universe, frozen in time and written into the fabric of space itself. The void is a fossil, a preserved relic of the universe's infancy, and its very emptiness is a message. It tells us that the distribution of matter is not random, but follows an intricate web-like pattern, with dense clusters of galaxies interconnected by filaments and separated by these vast, empty bubbles. The Boötes void is the negative space in the cosmic painting, and that negative space is just as important for defining the overall picture as the bright strokes of the galaxies themselves. The existence of such a massive void provides crucial insights into the nature of dark matter. We know that dark matter forms the invisible scaffolding of the cosmos, and its gravitational pull dictates where normal, visible matter will eventually clump together to form galaxies. The Boötes void suggests that in these regions the dark matter web must be exceptionally sparse. The gravitational wells here are too shallow to attract and hold onto the vast amounts of gas needed to birth new galaxies. Studying the void allows cosmologists to run sophisticated computer simulations of the universe's evolution, tweaking the parameters for dark matter and dark energy to see if they can naturally produce structures as large and as empty as Boötes. By matching their models to this real-world example, they can refine our understanding of these invisible components. The void, therefore, acts as a cosmic calibration tool, its emptiness serving as a precise measure against which we can test our theories of the universe's hidden mass. This leads us to the most fascinating informational aspect of the Boötes void. While it contains very little visible information in the form of stars and galaxies, it may be saturated with the invisible information we've been discussing. Its immense volume is filled with the quantum vacuum, its seething foam of virtual particles. It is permeated by dark energy, whose repulsive effect is likely the very reason the void is so enormous and continues to expand faster than the regions around it. And it is certainly crisscrossed by gravitational waves from ancient cosmic events that happened on its far distant edges. The information is not in the form of bright, localized points. It is in the subtle, diffuse properties of the void itself, the precise strength of the gravitational field within it, the minute temperature variations in the cosmic microwave background that arcs over its incredible expanse, and the specific way its emptiness affects the light from galaxies that lie billions of light years beyond. This light, as it travels through the void, is subtly stretched and warped by the void's gravity and the influence of dark energy, a phenomenon known as the integrated Sachs-Wolfe effect. By studying this distortion, astronomers can actually use the void as a giant natural laboratory to measure the properties of dark energy. The emptiness becomes a lens. The Boötes void transforms our understanding of cosmic information storage. It is the ultimate demonstration that information is not solely the property of luminous objects. A region of space can be almost entirely devoid of stars and yet be rich with data about the forces that shape the cosmos. It is a testament to the fact that the most important story isn't always written in the bright lights of the city. Sometimes it's written in the silent, expansive deserts between them. The great nothing is in fact a great something, a dynamic and informative part of the cosmic ecosystem that holds crucial clues about the past, present, and future of the entire universe. For centuries, artists have turned their gaze to the heavens not to paint the stars, but to capture the profound darkness that cradles them. This artistic pursuit is more than just a technical challenge of representing blackness. It is a deep human response to the sublime, a mixture of awe, terror, and wonder in the face of the infinite. The void in art is rarely presented as a mere absence. Instead, it becomes a powerful character in its own right, a canvas upon which we project our deepest fears, our most hopeful dreams, and our relentless curiosity about what lies beyond. From the swirling, star-flecked visions of Vincent van Gogh to the impossibly detailed nebulae in modern digital art, the cosmic void is portrayed as both beautiful and menacing, a place of serene tranquility and unimaginable danger. This duality reflects our own complex relationship with the unknown, giving form to a concept that science is still struggling to quantify. Nowhere is this cultural conversation about the void more vibrant and influential than in the realm of science fiction cinema. Filmmakers possess a unique toolkit to make the void not just visible but visceral. They use sound or the masterful absence of it to profound effect. Think of the breathtaking silence of the spacewalk in 2001, a space odyssey where the only sounds are the astronaut's own labored breathing and the mechanical whir of his equipment, emphasizing his terrifying isolation in the infinite. Or consider the overwhelming, bone-rattling roar of a starship's engines in Star Wars, a sound that could never travel in the vacuum of space, but that connects us emotionally to the power and adventure of cosmic travel. These sonic choices are not scientific errors, they are narrative tools that shape how we feel about the emptiness. The void can be a silent, contemplative cathedral inviting philosophical wonder, or it can be a roaring arena for epic conflict and exploration. These depictions fundamentally shape public perception, often planting the seed of cosmic or long before any textbook explanation of quantum foam or dark matter. Beyond sound, the visual language of cinema has given us enduring icons of the void's dual nature. The sleek, graceful starship Enterprise cruising past a vibrant nebula in Star Trek presents the void as a frontier of peaceful discovery and hopeful diplomacy, a place of breathtaking beauty waiting to be explored. In stark contrast, the cold, indifferent blackness surrounding the stranded spacecraft in Gravity is a terrifying antagonist. It is utterly silent, lethal, and devoid of mercy, a perfect representation of nature's absolute indifference to human survival. Then there is the ultimate cinematic manifestation of the void's terror, the black hole Gargantua in Interstellar. Based on the calculations of physicist Kip Thorne, its depiction was the most scientifically accurate visualization of a black hole ever seen at the time. The rendering of its glowing accretion disk and the gravitational lensing of the light from galaxies behind it created an image that was both terrifyingly monstrous and strangely beautiful, a cosmic maelstrom that warps not just space and time, but the very psyche of the characters and the audience. It became an icon of the void's immense, unknowable power. This artistic exploration extends far beyond the screen, permeating our entire cultural consciousness. The literary void of H.P. Lovecraft's stories is a terrifying abyss that whispers of ancient cosmic horrors, capable of driving those who gaze into it to madness. This stands in direct opposition to the serene, philosophical emptiness found in the meditative poetry of ancient Eastern traditions, which sees the void as a state of pure potential and peaceful unity. In music, the genre of dark ambient uses deep, droning soundscapes and vast echoes to create an auditory illusion of immense, empty spaces, evoking feelings of loneliness, contemplation, and sometimes dread. These diverse interpretations show that the void is a mirror. What we see in it says less about the nature of space itself and more about our own human condition, our fears of isolation and oblivion, and our hopeful dreams of discovery and connection. Ultimately, this rich tapestry of artistic expression does more than just entertain us. It prepares us. It provides an emotional and philosophical framework for the incredible discoveries being made by science. When a physicist talks about the quantum vacuum not being empty, or a cosmologist discusses the holographic principle, these ideas land on a mind that has already been primed by a lifetime of cultural exposure to the concept of the void. We may not grasp the mathematics, but we have already felt the emotional weight of the infinite through the art we have consumed. The artist and the scientist are engaged in the same great project, using different languages to explore the same profound mystery. One gives us the equations, the other gives us the awe, and together they provide a complete picture of our evolving relationship with the cosmic dark, transforming it from a terrifying nothing into a subject of endless fascination and the next great frontier for the human spirit. Staring into the profound emptiness of space, into the true scale of the cosmic void, does something to us. It's a deeply human experience, one that can be simultaneously unsettling and uplifting, terrifying and beautiful. This confrontation with the infinite can trigger a powerful psychological response, a complex mix of emotions that philosophers and poets have wrestled with for millennia, and one that modern psychology is only beginning to understand. It's a journey that begins with a feeling of sheer, overwhelming insignificance, a sensation so potent it even has a name: cosmophobia, the fear of the cosmos itself. When we truly internalize the numbers, the billions of galaxies, the trillions of stars, the unimaginable distances that light itself takes eons to cross, it's natural to feel a sense of personal smallness. Our individual lives, our daily worries and triumphs, can feel like a single, fleeting whisper in a roaring hurricane of cosmic activity. This feeling, often called the overview effect, has been described by astronauts who have seen the Earth from space, a fragile, blue marble suspended in a vast black nothingness. From that perspective, national borders vanish, and the conflicts that consume us seem trivial against the backdrop of the infinite. This isn't a negative feeling, it's a profound dose of perspective. It can crush the ego, but in doing so, it plants the seeds for a deep and genuine humility. We are reminded that we are not the center of the universe, but a tiny, conscious part of a system of majestic and incomprehensible scale. This humbling realization can be incredibly liberating, freeing us from the weight of our own self-importance and inviting us to see our place in the grand scheme of things with new eyes. But this initial feeling of smallness rarely stops there. For many, it quickly blossoms into its opposite, a profound sense of awe. Awe is that breathtaking emotion we feel in the face of something vast that transcends our current understanding of the world. It's the feeling you get standing at the edge of the Grand Canyon, listening to a symphony or holding a newborn child. The cosmic void is perhaps the ultimate catalyst for awe. It is the vastest thing we can possibly contemplate. This feeling of awe has tangible psychological benefits. Research has shown that experiencing awe can make us more curious, more creative, and more connected to others. It shifts our focus away from our narrow, individual concerns and toward the bigger picture, making us more likely to engage in collaborative, generous behavior. By contemplating the void, we are essentially giving our minds a workout in awe, stretching our capacity for wonder and expanding our sense of what is possible. This expansion of mind is a direct fuel for creativity. The unknown has always been the artist's muse and the scientist's catalyst. The blank canvas, the empty page, the unsolved equation, these are all small voids waiting to be filled with something new. The cosmic void is the ultimate blank slate. It invites speculation, imagination, and the courage to ask, what if? Science fiction from the works of Arthur C. Clarke to the visuals of Interstellar is a testament to this creative power. The void forces us to think in ways we normally wouldn't, to connect ideas across disciplines, and to envision realities beyond our everyday experience. It pushes the boundaries of human thought, inspiring not just stories, but real scientific breakthroughs as we strive to fill the gaps in our knowledge with new theories and daring experiments. Of course, this journey can also lead to a more challenging path, existential reflection. Gazing into the abyss can make us question the very point of our existence. If we are so small and temporary, do our lives have any meaning at all? This line of thinking can be daunting, but it is also the source of our greatest strength. The void doesn't give us answers, it gives us the silence necessary to ask the most important questions. It was in the face of this apparent meaninglessness that philosophers like Albert Camus found a defiant purpose. If the universe is indifferent, then it is up to us to create our own meaning, to find value in our relationships, our passions, and our contributions to the human story. The void, in its utter neutrality, gives us the ultimate freedom to define what matters. Our lives aren't insignificant because the universe is large. They are significant precisely because we, in our fleeting moment of consciousness, can choose to make them so. We are the universe's way of understanding itself, and that is a role of incredible importance. So, the next time you find yourself under a clear night sky, take a moment to really look at the darkness between the stars. Don't just see an absence, feel the weight of that space, the depth of that silence. What does it bring up for you? Does it make you feel lonely, or does it make you feel connected to something magnificent? Does it spark a frantic curiosity or a peaceful acceptance? There's no right or wrong answer. This personal, emotional response is a vital part of the exploration. It's what transforms cold facts about light years and quantum foam into a living, breathing relationship with the cosmos. We'd love to hear what you feel. Share your thoughts in the comments below. Let's explore this vast internal landscape together, just as we strive to map the infinite external one. We have journeyed through a landscape of ideas that has completely redefined the very concept of nothingness. From the quantum vacuum's seething foam of virtual particles to the invisible gravitational architecture of dark matter, from the cosmic fossil light of the CMB to the ripples of gravitational waves in spacetime, a single, stunning picture emerges. The void is not an empty stage. It is the most dynamic and information-rich character in the entire cosmic play. Each thread we've pulled on, quantum physics, cosmology, information theory, and even philosophy, has led us to the same inescapable conclusion. The apparent emptiness between stars is, in fact, a plenum, a fullness of such profound activity that its informational capacity may very well dwarf the combined output of every star that has ever shone. Think about how these disciplines converge to paint this picture. Quantum mechanics gives us the fundamental unit of this cosmic data stream, the bit, represented by every probabilistic flicker of a virtual particle. Cosmology shows us the scale, revealing that dark matter and dark energy, the primary constituents of the universe, are not concentrated in galaxies but are diffuse, permeating the vast expanses and shaping the cosmos from the shadows. The holographic principle, born from the paradoxes of black hole physics, provides a revolutionary framework for how this information is stored, suggesting that the entire three-dimensional universe we experience could be a projection from a two-dimensional surface encoded at the edge of everything. And information theory gives us the language and the mathematics to quantify it all, showing that disorder and information are two sides of the same coin, and the high entropy potential of the quantum vacuum represents a near-infinite data reservoir. This is not just a story for physicists. It is a profoundly interdisciplinary narrative that bridges the gap between the abstract and the tangible, the theoretical and the technological. Philosophy challenges us to consider what information even means on a cosmic scale, and whether a conscious observer is needed to bring it into being. Technology, through instruments like LIGO and the James Webb Space Telescope, is providing the empirical evidence, translating these mind-bending theories into measurable data. We are witnessing a grand synthesis where the questions asked by ancient philosophers about the nature of the void are being answered with the mathematical rigor of modern science, and those answers are, in turn, inspiring the next generation of engineers to dream of technologies that could one day tap into this cosmic network. This synthesis allows us to see the big picture with stunning clarity. A star is a brilliant, localized event, a temporary, low-entropy engine burning through its finite fuel to broadcast a specific, structured story. It is a masterpiece of cosmic information, but the void is the library that contains not only that story but every possible story. It is the background medium, the quantum fields, the dark matter web, the imprint of the Big Bang, and the fabric of spacetime itself. Its information is not finite or localized. It is eternal, ubiquitous, and woven into the fundamental code of reality. The stars are the fireworks, the void is the gunpowder, the laws of chemistry, and the very space in which the explosion occurs. By weaving these threads together, we move from seeing isolated phenomena to understanding a unified, interconnected cosmos where the darkness is not the absence of information, but its ultimate source. This holistic view prepares us for the final step, reflecting on what this incredible revelation means for our understanding of reality and our place within it. So as we reach the end of our journey, let's pause and look back at the path we've traveled. We began by staring up at the familiar night sky, at those brilliant points of light we've admired since the dawn of humanity. But then we turned our gaze to the profound darkness between them, and we asked a simple yet revolutionary question: what if that darkness isn't empty? What we discovered along the way is a truth more astonishing than any science fiction. The void is not a barren wasteland. It is a cosmic plenum, a dynamic and teeming medium, buzzing with quantum fluctuations, woven through with the invisible threads of dark matter and energized by the mysterious push of dark energy. It is a universe-sized hard drive, a holographic projection, and the ultimate historical archive all at once. This perspective doesn't just add a new chapter to our understanding of the cosmos. It fundamentally rewrites the entire book, transforming our view of reality from the ground up. This realization shifts our cosmic center of gravity. For so long, we have seen the stars as the main actors in the cosmic drama, the brilliant generators of light, heat, and the very elements of life. And they are, but we now see that they are actors performing on a stage of unimaginable depth and complexity. The true story of the universe is not written solely in their fusion fires. It is encoded in the fabric of spacetime itself, in the quantum foam that fills every cubic centimeter of nothingness, and in the gravitational waves that ripple silently through the vast expanses. The stars are the spectacular, localized events, but the void is the constant, eternal background, the foundational reality that contains the instructions for everything. It is the silence that gives meaning to the symphony, the canvas that holds the painting. To understand that the emptiness holds more than the full is to undergo a complete Copernican revolution of the mind, where the background becomes the foreground and the void becomes the source. This journey leaves us not with a final answer, but with a deeper, more profound sense of wonder and a renewed commitment to questioning everything we think we know. It brings to mind the words of the great physicist James Clerk Maxwell, who said, "The only laws of matter are those which our minds must fabricate, and the only laws of mind are fabricated for it by matter." We are part of this beautiful, mysterious feedback loop, the universe trying to understand itself. Our quest to decode the void is the ultimate expression of that self-awareness. It is a humbling reminder that the greatest mysteries are not always hidden in the light. Sometimes they are waiting for us in the dark, inviting us to look closer, to listen more carefully, and to never stop being curious about the infinite unknown that surrounds us. Your thoughts and perspectives are a vital part of this ongoing exploration. What did you find most mind-bending about this concept? Does the idea that the void could hold the universe's deepest secrets change how you see the night sky? Share your reflections, your questions, and your own sense of wonder in the comments below. Let's continue this conversation together. If this journey into the cosmic dark has expanded your view of reality, please give this video a like, subscribe to the channel, and hit the notification bell so you don't miss our next adventure to the frontiers of knowledge. The cosmos is full of mysteries waiting to be uncovered, and we can't wait to keep exploring them with you. Thank you for watching, and never stop looking up and wondering what's out there.